First of all, I'll introduce myself. My name is Brayden McNeill. I'm the Technical Sales and Marketing Lead here at Aquanty. I can be your primary point of contact for any questions you have about HydroGeoSphere. My entire job really here at Aquanty is all about helping new users to, learn about what HydroGeoSphere can do, adopt it for new projects. I am basically the primary point of contact for training, tech support, sales, and marketing. Thanks for joining me today. We're here for my monthly training session, an introduction to integrated hydrologic modeling with HydroGeoSphere. The purpose of this training course is really to focus on the practical aspects of using HydroGeoSphere. I will start with a brief introduction to the sort of design philosophy about HydroGeoSphere, a quick review of its key features and differentiators compared to other hydrologic models. But yeah, pretty soon we'll get into the nuts and bolts of actually using HydroGeoSphere, providing an overview of the key executables that are at the heart of the HydroGeoSphere workflow, and perhaps most importantly of all, how to put together HydroGeoSphere model input files. The training sessions that I like to deliver, I always like to deliver them relatively informally. If you have questions at any point in time, feel free to raise your hand or put a question into the chat box. I'm more than happy to take questions as they come up. Before we really get rolling here, I do also just want to quickly note that the training session is being recorded today, so I will be sure to get a copy of this recording available up and loaded onto our YouTube channel as soon as possible, and we'll be sure to email everyone after the fact with a link to that so that you can review at any point in time should you need to get a refresher. That also means if you have any other commitments this afternoon or this morning from wherever you're calling from, it's okay. You're always going to be able to review this later on, so no problem if you're only able to stick around for half the training session today. Gonna turn my screen, or rather my camera, off here. I usually find it just a little bit distracting, but I wanted to give everyone an opportunity to sort of put a face to my name rather. So let's get things started. So we start with an overview of HydroGeoSphere, the sort of philosophy of its design and an overview of features. So traditionally, in the world of hydrologic modeling, surface water models and groundwater models have been done separately. Surface water modelers and groundwater modelers have kind of done their own thing, and basically, these models would only represent a single component of the hydrologic cycle. If you were building a groundwater model, the impact of surface water systems would have to be represented in that groundwater model as boundary conditions or mathematical forcing functions. And the same is true in the opposite direction for a surface water model. Groundwater systems would have to be, or the impact of groundwater systems would have to be applied as a forcing function. The big drawback here is of course the fact that there's really no way of allowing the groundwater and surface water system if you're only simulating one system, to have any sort of really dynamic feedback between them. The framework for coupled models that integrate multiple different types or sets of governing equations to represent flow through different parts of the hydrologic cycle. The framework has been around for a long time, but in the early days of hydrologic modeling, computer resources were somewhat limited, and so loosely coupled and tightly coupled models were not all that popular sort of in the early days of hydrologic modeling. But of course, as computers have become more and more powerful, it becomes more and more feasible to take a sort of a more comprehensive and physically realistic approach to simulating the movement of water. And this is really what HydroGeoSphere is all about. So here we have a little bit of a sketch that kind of shows the landscape of different hydrologic models. At the top left, we have surface water only models, the simplest versions of which are lumped hydrologic response units. These essentially are statistical relationships, right, between rainfall and runoff. They're not really, in my mind, proper sort of model. When I use the word model, usually what I'm thinking about is a system of distributed partial differential equations where we take a real world area, we will build a digital mesh or a digital grid representing that area, and we will then apply a series of PDEs, partial differential equations, based on some governing equation of flow. to simulate the movement of water either over land or underground. So this distributed PDE system is basically the de facto standard for all groundwater models, the most common of which is ModFlow. But different types of groundwater models, right, they only look at a limited picture of the world of terrestrial water flow. ModFlow only handles fully saturated groundwater flow. PHFlow is probably the most common variably saturated flow engine, but of course it's limited to, you know, the variably saturated and saturated groundwater system. Doesn't incorporate surface water flow. The real differentiator between HydroGeoSphere and most other integrated hydrologic models is in the coupling aspect. So a loosely coupled model is really just a series of models that are able to communicate with each other. So you'll have a system of equations that's built up into a matrix, you know, and solved iteratively for surface flow, and then some information can then be communicated from that surface model to the groundwater system, and they go through sort of a multi-layered sort of iteration approach to solving a wider. It's sort of like grouping multiple models or modules together, whereas a tightly coupled model like HydroGeoSphere is fully integrated, tightly coupled, meaning it's a single matrix of equations that contains different. The matrix of equation contains different regions with different governing equations within it. So we'll dig into that a little bit more here in a minute as well. There's really three things that distinguish or differentiate HydroGeoSphere from the rest of the pack. The first is that it's a control volume finite element simulator. What this really means is how is the spatial and temporal discretization applied with a HydroGeoSphere model? How do we actually build out that mesh of like a digital twin mesh of a landscape, and how do we apply the governing equations? How do we discretize them over space? The second thing is that it's fully integrated, right? So what this means is that there are multiple different equations of flow that are operating under the hood of a HydroGeoSphere model to represent the movement of water through different parts of the system. There's a variably saturated groundwater equation, there's a separate equation for surface water flow, and yet another equation for evapotranspiration or channel flow, et cetera, et cetera. And the third distinguishing factor is that tightly coupled numerical implementation. What is a control volume finite element simulator? What is the discretization approach that HydroGeoSphere uses? Well, if we consider a random function, i.e. the red line that you see on the page here, there's a lot of different ways that we can represent this analytical solution or an analytical function and discretize it spatially, right? The simplest approach to discretizing these types of equations, in the world of groundwater modeling, it would be, you know, Darcy's equation or Richard's equation. The simplest approach is called the finite difference method. So what we do here is we break up the spatial domain into a series of discretized chunks. We then evaluate the solution at the endpoints of these intervals, where they're approximated using an iterative solver approach. So those are the blue dots, which approximate the red line solution. And it's assumed that the solution at those blue dots extends beyond the individual exact spot where it is solved, and is sort of constant over the cell around which that point resides, basically. So this is a relatively computationally simple approach to evaluating a function, but it has a couple of drawbacks. It's not locally mass conservative, which means you can have local mass balance errors. And there's also a spatial discontinuity in the solution, right? So if you go from one point here to the next point, the neighboring point, there's this large jump in the hydrologic solution. The next approach that we can use is a finite volume method. So here, what we're doing instead of evaluating the function at a singular point in space is we're actually evaluating the integral of the function, or evaluating the volume or the area under the line over an element itself. So these blue lines here represent sort of, this is by no means super accurate, I just did a little bit of a sketch, but the blue lines here are meant to represent sort of the equivalent area under the red line within each of these elements. This is a little bit more computationally intensive, generally gives you a better, more accurate representation of the overall flow solution because it is locally mass conservative. You avoid having these local mass balance errors, but you still have the spatial discontinuity in your solution. Yet another more complex approach to discretizing equations is by using the finite element method. So here, this is much more computationally intensive. What we're actually doing is we're using linear finite element base, or linear, sorry, what's the terminology? Linear basis functions, essentially. We're trying to approximate as best as we can the red line over the interior of an element by using a straight blue line, right? So here we're able to get a really pretty good representation of the overall sort of nature of the function over the space that we're looking at. But this approach is also not locally mass conservative and has slight discontinuities in the spatial solution, right? You can still have areas where the solution jumps quite a lot from one point in space to the next. So this brings us to the final discretization approach, the control volume finite element method. And this is what HydroGeoSphere is doing under the hood. It's really the same as the control volume finite element method that we saw here, with one extra caveat. And that is being that we enforce continuity. We enforce the blue lines to meet at the edges of elements. So not only are we evaluating the linear basis function over the course of an element, but we're also taking into account basically neighboring elements as well as we discretize the solution. This is the most computationally intensive approach to discretizing these types of governing equations, but it is locally mass conservative and gives you spatial continuity in the solution. And as well, I'm aware that visually, this looks a little bit better than this does, but at the end of the day, the amount of spatial discretization that you apply is entirely up to the user. And so even though this visually, just at a glance, doesn't look quite as good as this is the overall better approach. So HydroGeoSphere is based on a control volume finite element discretization. We are applying governing equations at nodes. We build a wire mesh to represent a watershed or the model area of interest. The governing equations themselves are being applied at individual nodes. So those would be the black points that you see in these two images here. Every node will have an associated nodal control volume, which extends basically from the node into all of the neighboring elements. And the actual governing equations themselves, the solution, is basically, it's spatially discontinuous over this red shaded area. Basically, the actual solution, given that the solution is applied directly at these nodes, and it's basically interpolated between neighboring nodes, so you have a lot of spatial variability sort of in the solution. Now, HydroGeoSphere is also a tightly coupled model. So when you have a fully integrated model, you're going to be applying multiple different governing equations of flow to represent the movement of water in different parts of the model, whether it be surface flow and subsurface flow. In a loosely coupled model, what you really have are two or more models that have linkages between them and are able to communicate with each other. So if we consider this system here, this loosely coupled system, we have a surface model and we have a subsurface model. These blue lines just indicate some sort of virtual distance. In reality, the locations of the surface nodes and the top layer of the subsurface nodes, they are superimposed on the exact same location, right? So the blue line is sort of just like a virtual distance to illustrate that they're, even though they're superimposed on the same location, they are distinct from each other. So in a loosely coupled model, and any model with a system of partial differential equations, we will build up a matrix of equations, which is going to be solved iteratively. So on the left-hand side, we have our matrix of coefficients. And then here we have a head vector, which contains all of the unknowns within our model. So H1 to H9, these are hydraulic head values at the different nodes within the matrix. And then our Q matrix over here is meant to represent the impact of specified changes in storage or fluxes. So essentially the impact of boundary conditions. So when we have a loosely coupled model, we actually have two distinct sets of or matrices of equations. And you'll notice that both of these matrices, the subsurface model and the surface model, they both contain H1 through H9. That's because, again, these nodes are superimposed in the same location and therefore need to have a sort of shared hydraulic head value. In a loosely coupled system, what we really do is we iteratively solve the surface model, and then we take the results of the solution. Once it converges on a solution, we take H1 through H9 and we map them onto the head vector of the subsurface model as the initial condition for the subsurface model to go through its series of iterations and come to a solution. Once the subsurface model converges on a solution, the head values, H1 through H9, are compared to the previously solved H values or head values for the surface model. And if they don't match, then the head values from the second iteration here in the subsurface model are mapped back onto the surface model. The surface model goes through another round of iterations. The heads from the surface model are then mapped onto the subsurface model. And this process just continues and continues and continues until they go through at least one iteration where the H1 through H9 in both matrices of equations match. This approach, this multi-level iterational approach, just introduces a lot of potential failure points, basically. In comparison, what HydroGeoSphere does is it is based on a single global matrix of equations that has different underlying governing equations of flow for subsurface flow, for surface flow, for evapotranspiration. And what HGS does is introduce additional off-diagonal terms that allows for basically information from a node that is shared in both the surface and the subsurface to communicate with each other, basically. So this is a more numerically sophisticated approach to building out a system of integrated hydrologic simulations. It has less convergence difficulty, fewer failure points in the overall system means that you're going to have a higher likelihood of actually converging on a solution, which means you're going to have a higher likelihood of successful modeling project. And in general as well, these types of approaches tend to be faster than a loosely coupled system. Now in HydroGeoSphere, there's actually two approaches to how this can work. The default is what we call a common node approach, where these red nodes represent a point in space where both surface and subsurface equations are going to be solved. In the common node approach, there really truly is only one node at the location of these red dots. And that one node has to satisfy multiple governing equations of flow. This can be a little bit numerically unstable. So what we actually recommend as a general approach for all users is to use what we call a dual node approach. So with the dual node approach, you'll have two nodes, right, superimposed onto the same location, just like I said before, basically. You'll have one node for surface flow, for example, this node right here, and another node for subsurface flow. Given the fact that there are two nodes, even though they are spatially superimposed on the exact same location, the fact that you have two nodes allows you to carry two hydraulic head values. This means that you have a higher number of unknowns in the overall matrix of equations, and yet the entire system is more numerically stable and therefore generally faster to simulate. It also supports the explicit flow of water between surface and subsurface model domains. So that exchange is just based on this equation up here, which essentially is a form of Darcy flux. It's driven by a head gradient between the two nodes, a coupling distance, L exchange here, which is defined by the user, and then the hydraulic conductivity, which is basically adopted from the hydraulic conductivity of the underlying soil. The third major fundamental characteristic of HydroGeoSphere is that it is fully integrated. So here, just to quickly provide an overview, in the subsurface, HGS handles a 3D form of Richard's equation. The 3D form of Richard's equation incorporates this Darcy-Buckingham equation for internodal fluxes. This internodal flux calculation includes a relative permeability, Kr. That Kr is based on soil saturations. So the way that relative permeability is handled in HydroGeoSphere, on this next slide we see it's basically based on either the Van Gnukten or the Brooks-Corey equations, or users can define a tabular relationship between soil saturation and pressure head and the saturation and relative hydraulic conductivity. So we'll talk more about that later. I'm not going into too much depth here on the theory side of things. It's all fully documented in our reference manuals, so this is something that everyone, if you're going to be using HydroGeoSphere professionally, you'll read up on. This is the actual discretized equation, Richard's equation, so the discretized form of the system of equations that's being applied for the subsurface. Again, I'm not going to dwell on it just in the interests of time. In the surface domain, we handle surface flow using the diffusive wave equation. So this is an approximation of the Saint Venant equation. It assumes that inertial terms are less than gravity, friction, and pressure terms. So what this basically means is that in HydroGeoSphere, the surface flow equation does not incorporate a momentum or an inertia component. What this means is that HGS is not really suitable for really fast flowing simulation processes. So for example, flash floods, anything involving erosion, sedimentation, scouring, these types of things are not really possible with HydroGeoSphere, given that this equation doesn't carry that momentum term. But it is a very valuable approach to modeling sort of slow, stable, gradual surface flows, the movement of water in rivers, floodplains, and the like. In terms of the diffusion wave equation, the internodal flux component here, Q naught, there's an important component in here, which is the N term, Manning's friction coefficient. This is one of the critical parameters that will impact surface flow rates in a HydroGeoSphere model. We'll take a closer look at model parameters and how they're applied to your model a little later on. Again, we have our discretized equations here, but I'll just refer you to the theory manual so you can see section 3.5 here. And yeah, all of our equations include these discrete coupling terms, which allow for that exchange of water, the dynamic exchange of water between different model domains. So these exchange terms play into those additional layers of off-diagonal coefficients within your matrix of coefficients, but it's kind of getting into the weeds. We don't really need to know too much about the internal structure of the matrices. HydroGeoSphere also supports solute transport. So we've got our coupled advection dispersion reaction equation listed out here for surface and subsurface flow. I'll just quickly note, again, the ADRE, or the solute transport equations, incorporate this explicit exchange term, which means that solute mass is able to flow freely between the surface and subsurface, or the surface and channels, or the subsurface part of the model in discrete fracture networks, et cetera, et cetera. And finally, evapotranspiration. So just quickly, the ET process in HGS is based on a 1975 paper by Christensen and Jensen. It's a fully distributed ET in 3 dimensions. The way it works is you'll apply a PET rate as a boundary condition to your model. This PET rate is typically calculated externally as the total potential for evapotranspiration based on factors like land use classification and that type of thing. The actual evapotranspiration rate that's going to be applied to the nodes in your model is calculated by reducing that PET according to this Christensen and Jensen formulation, which is going to subject the actual evapotranspiration rate to things like vegetation characteristics and the saturation, the actual availability of water at a node-by-node basis. The actual evapotranspiration is applied in 4 components, and again, it's fully spatially distributed in 3 dimensions. So there's a canopy evaporation, a surface evaporation, and then a subsurface evaporation and transpiration components. So these are all separately calculated and applied based on the way that you parameterize the Christensen and Jensen sort of process. So those are the 3 major things that really set HydroGeoSphere apart from the pack. It's a control volume finite element simulator. It's using the most advanced method of discretizing these governing equations. The fact that it's fully integrated. There are multiple governing equations of flow that are sort of inherent into HydroGeoSphere in the way that water moves within a HydroGeoSphere model. And finally, it's tightly coupled. All these different governing equations of flow are applied to a single global matrix of equations. Why do we take this integrated approach? Well, in general, I've already kind of alluded to this, but using a fully integrated approach allows for dynamic feedback between different parts of a hydrologic system. If you're looking only at groundwater flow or only at surface water flow, the impact of the opposite side of the coin is something that you have to apply as a mathematical forcing function, as an input to your model. By building a fully integrated hydrologic model, you can really let physics take the lead and basically allow for dynamic interactions between the groundwater and surface water systems. This physics-based approach is really a strong sort of overall approach to simulating hydrology in quote-unquote unknowns. So this could be, under unknown climate conditions. If you're estimating a recharge rate as a boundary condition for a groundwater model, for example, the way that you calculate that recharge rate is going to be predicated on historical observations. You don't need to do that with HydroGeoSphere. If the climate changes, the physics of water flow does not change, right? The only thing that really is going to change is the climatological forcing, the precipitation rates and whatnot. So HydroGeoSphere is an extremely strong this physics-based approach inherent to HydroGeoSphere is a strong approach to simulating watersheds under a changing climate. It's a really strong approach to design or testing design topographies, for example, flood mitigation measures, mine operations, that type of thing. It's also a really strong approach for simulating catchment systems or hydrologic systems that have sparse observation data. In principle, what we really do with a physics-based hydrologic model is we build an accurate representation to the best of our ability of the spatial discretization of soil types, land use classification types, et cetera, but then we just tell the model directly what the precipitation and climate characteristics are. Precipitation data is directly observable and measurable. There's very little uncertainty in precipitation rates compared to, for example, groundwater infiltration rates. We just rain on the model and let the water flow where it may. Let the model tell us where the water goes. We don't have to overly constrain the model with boundary conditions in that sense. So this is what HydroGeoSphere is all about. We simulate the entire terrestrial portion of the water cycle, major emphasis on physics with every piece of the puzzle, with every governing equation, and minimal use of empirical relationships wherever possible. We've already talked about the basic level capabilities, 2D diffusive wave equation for surface flow, 3D Richards equation for subsurface flow, 3D evapotranspiration. We can also incorporate discrete fracture networks, which are going to be calculated also using a form of Richards equations. We can incorporate one-dimensional hydraulic features such as overland or sort of superficial channels, tile drains, wells in the subsurface. These will potentially be modeled using a number of different equations or governing equations. Almost all of our model domains or different governing equations support both spatially, of course, but also temporally varying domain properties. So for example, we can apply time-varying hydraulic conductivity to represent the impact of pore-water freezing and thawing, for example. We support that dual node formulation for explicit exchange of water between all model domains. We support solute transport, both reactive, density-dependent flow, geothermal energy transport processes. We have a number of native or inbuilt winter processes, pore-water freezing and thawing, native snow melt and accumulation. There's really a lot of advanced numerical methods. We kind of try to expose every piece of the numerical simulation criteria to the end user. So if you're a really experienced modeler, you will have full control over all of the settings for the numerical solution. Excuse me. We support multiple solver types. Locally, you can parallelize HGS models for faster model runtimes. It's all based on an adaptive time stepping routine, which we'll get into a little bit more. And we just continue to try and add more and more advanced features, such as particle tracing, dynamic meshing, where we can modify the topography of a model over time, the hydraulic mixing cell formulation, which is a really great way of tracking discrete sources of water throughout a model. And just, the feature list goes on and on. We've demonstrated HGS is a good, it's a valid simulation engine at basically all scales, from the column scale all the way up now to major river basins and even continental scale applications. But of course, the scale of the model is going to, or I should say the application itself, your research goals, is going to dictate the scale of the model, right? And of course, you're always going to be limited by the reality of computational resources. So here we have an image of the Grand River watershed, which I'm not exactly sure. I think is something like 25 or 30, maybe more, thousand square kilometers. And in this mesh, we have a total of 3.5 million total nodes. This is probably about 3.5 times higher than I would recommend any new HydroGeoSphere user to aim for. HydroGeoSphere model runtimes are always going to be long compared to other models just by virtue of the nonlinear nature of the governing equations of flow. So wherever possible, I always caution new users to try and take a sort of austerity mindset when it comes to building your models. Try and keep them simple at first. Once you have more experience with HydroGeoSphere and you have more tips and tricks and sort of tools in your tool belt to squeeze out every bit of efficiency that you can with HydroGeoSphere, then you'll be able to do more. You'll be able to build more complex models while maintaining a reasonable model runtime. But certainly to start with, try to keep things simple. Don't bite off more than you can chew, right? As my mother would say. This video here is a simple cross-sectional model that just serves to illustrate what HydroGeoSphere really can do. You'd find that this type of simulation would be essentially impossible to actually model with almost any other simulation platform on the market. It's quite simple. It's a small cross-sectional model, but it is illustrative. So in this model, we have a basic cross-section with 2 potholes, and we have some water flowing in from the upland area here, as well as a bit of precipitation. But what we see here is that the landforms themselves are dynamically filling, right? So if you're coming from a background of mod flow, just know that lakes, rivers, ponds, they do not have to be defined as boundary conditions in your model. If you can accurately represent the topography or the bathymetry of the location of a lake, then that lake should appear as a product or an output of your model. As long as your climatology is right, you're applying the right amount of precipitation to the watershed, the surface flow network should, the physics of water movement will reproduce the actual surface flow network. So we see these potholes are dynamically filling and overtopping and flowing downhill. We see the 3-dimensional movement of the wetting front through the unsaturated zone. Around the middle elevation here, there's actually a clay lens. And so what we end up seeing here as the wetting front progresses is that we've got perched aquifer forming. And through this clay lens, we have a number of randomly seeded fractures. And so you can start to see the preferential flow of water through those fractures to the lower aquifer. So again, it's something that is quite easy for HydroGeoSphere to handle, but I can tell you with confidence that there's really no other models on the market that would be able to handle this with such sort of fidelity to the physics of flow. And again, we've already seen this quick animation, but it just kind of, again, serves to drive home the point that in HGS, groundwater flow and surface water flow are one and the same, right? They're fully integrated and fully dynamic, right? So surface water changes will automatically impact the distribution of heads in the subsurface and potentially vice versa as well. So that's my quick sort of intro to the philosophy and design philosophy behind HydroGeoSphere and the features and capabilities. We're shifting gears now into the more practical. So the first thing that I like to do is to do a quick review of some of the key resources that are available to new users once you install HydroGeoSphere, and point out where you can find example models to review. And yeah, also the user manuals are very important as well. And as we go through the rest of the training session here, I'm also just going to be flipping back and forth repeatedly between the actual slide deck and a number of different programs locally here on my computer. So just going to quickly open something up here. So first of all, the default installation folder. When you install HydroGeoSphere, it'll be found under the Program Files folder. In this folder, you'll find a couple of resources that are very, very helpful. The first thing is the docs folder contains 3 manuals. These are our 3 user manuals for HydroGeoSphere. They each cover sort of a different type of information. The first is our theory manual. As you can probably guess, the theory manual introduces the theory of HydroGeoSphere. It will provide in Chapter 2, Theory, review of all of the different governing equations of flow that are present in HydroGeoSphere for both subsurface flow, in the porous medium, in discrete fractures, in 1D hydromechanical coupling, the governing equations of flow for surface flow, for one-dimensional hydraulic features such as channels, tiles, drains, wells, how flow is coupled between different model domains, an intro to the solute transport simulation, governing equations, etc., etc. Chapter 3 is all about the numerical implementation of HydroGeoSphere. So how do we actually discretize these governing equations? An introduction to the control volume finite element method, the discretized equations themselves. Again, how are we coupling flow between different model domains on a nuts and bolts basis in terms of how the actual system of equations fit together on a sort of a discretized equation basis. And then finally, a section on numerical techniques. How is the governing how are the matrix of governing equations, how's the matrix of equations constructed and solved? You don't have to read this manual front to back. There are certainly going to be sections that may not be of interest to you. For example, if you're not running a solute transport model, if that's not what you're interested in using HydroGeoSphere for, you don't have to read those sections of the model, of the manual. But with that being said, if you're going to be using HydroGeoSphere for research or for professional consulting services or whatever the case might be, it is always important to be familiar with the tools that you're working with. And so a good place to start with HydroGeoSphere potentially is with the theory manual, taking a bit of a deep dive into the key sort of sections that will impact your work. Our second manual that I'll highlight is the verification manual. This verification manual exists to basically provide a plain English description of all of the example models found in this subfolder of the installation folder. So every subfolder that you see here is an example HydroGeoSphere model that can serve as a blueprint for you to learn HydroGeoSphere. All of these different models were basically designed. We use these verification models, as the name implies, to verify that HydroGeoSphere is still working every month when we release a new version. We will run each of these models and make sure that the solutions that are produced are still accurate. So each of these folders is based on a published analytical solution or model from the literature. And what we're going to come to see pretty quickly with HydroGeoSphere is if we open one of these model folders up, we're going to see just a handful of text files. The key one is the .grok file. This is just a quick tip for you. If you're going to be using HydroGeoSphere, I always recommend that you view your project folders using the details option in Microsoft Windows Explorer. That way you can organize your project folder by file type. I also recommend clicking View, Show, File Name Extensions, and this is going to help you to see. You'll notice already that there are 3 files here that all have the same name, Abdul. They just have different file extensions. So this can help you to navigate your project folder. But if you open up any one of these verification models, you'll see that the folder just contains a few text files. If I open up this text file here, abdul.grok, this is the primary model input file. HydroGeoSphere does not have a graphical user interface. The entire workflow is predicated on the process of building a text-based model input file and then running a series of executables directly from the command prompt, which will process this text-based file into the matrix of equations and then solve the matrix of equations. And then finally, we will run a third executable to reformat model outputs. Now, because a new user is going to open up these files and is not going to immediately understand what it is that they're looking at, this is what the verification manual is really all about. Every single one of the files or example models in the verification folder has an associated section here. If we open up the section on Abdul, for example, we can just click here. At the beginning of the section, we see a note that the verification problem described in this section corresponds to the Abdul snowmelt, Abdul thermal, and Abdul transport test cases found in the verification folder, right? And then you basically just get a plain English description, maybe some images, a couple tables that list the associated parameters for this model, and then typically as well, you'll get some model outputs. So the verification manual describes the verification tests. But the verification tests themselves are an extremely helpful tool because each of these input files basically represents a blueprint for your own HydroGeoSphere models. Let's say, for example, I'm really interested in the geothermal energy transport processes in HydroGeoSphere. Well, I can go to the verification manual, find the subsection on heat transfer, and I can see that the Ward, the temp F, the Mayer, the Yang, and the thermal Molson test cases, they all have, to some degree or another, geothermal energy transport as a sort of core component of these models. So each one of these models, each one of these verification tests, then becomes a learning tool for me to review. I'm just going to open up the Ward input file, and as you look through more and more model input files, you will come to encounter new commands. For example, the specific heat capacity of water. The text-based input files for HydroGeoSphere use a command-based language that is described in the third manual, the reference manual. But each of these commands becomes a new tool in your tool belt when it comes to building your own models. So these verification tests, again, they basically represent a number of pre-built models that you can review and learn from and sort of use them as blueprints for building your own models. The last manual is potentially the most important manual for a new HydroGeoSphere user, our reference manual. It's also the longest. It's over 450 pages at this point. You definitely do not need to read this entire manual front to back, but if we do a quick scroll through the manual, you will start to see that the manual just basically consists of page after page after page of this sort of repeating set of these are commands. So you have these, a solid line followed by this text in this format. This is a command that you can apply in your model input files, and it does something. In this case, right chosen nodes, you would be required to also provide a file name, and then it writes the node number of the currently chosen nodes to the specified file. ... end of description, on to the next command. So this entire manual is hundreds and hundreds and hundreds of pages of commands which users can use to build their models. So this is your toolkit, right? This is really the baseline, the foundational sort of pieces of how you build your own HGS models. If we open up one of these verification tests, line by line by line here, every single command that you see in here is echoed somewhere in that reference manual. And so part of the process of learning HydroGeoSphere is just reading through these input files. For the most part, the command-based input language is relatively intuitive. For example, the command boundary condition type critical depth, this is the basic process for defining a boundary condition. In this case, the type is going to be a critical depth boundary condition, and it's going to be applied to a certain segment set that is called outlet. If we move further down, we can see other examples of commands. For example, the Newton absolute convergence criteria command defines the Newton absolute convergence criteria for your simulation. This is an error metric that determines how the Newton iterative solver will behave. Moving further down, yet again, we have a command here, output times, with a number of times listed, and then finally an end command. Even without checking in the manual, you can probably guess that this command has something to do with when model results will be output, right? This is where these are times at which model results will be written to a file. The command make observation point followed by these two lines of text. Just by looking at it, and you probably are starting to think, well, maybe these are coordinates, and you would be right. This command basically flags the node closest to these coordinates and writes detailed observation data to a file that would contain this name. So these are critical resources for new users, right? The fact that there are these three manuals, potentially most important of which is the reference manual, which contains a description of every single command that can be used to define a HydroGeoSphere model within the context of these model input files. And the verification tests, right? There's about 35 to 40 individual example problems included on installation that you can use as learning tools, basically. So with that being said, let's explore the actual workflow. So in HydroGeoSphere, and this is a simplification, there's generally 5 steps. The first is to configure or write a grok file. So this is easier said than done. Fortunately, we have, like I said before, about 40 working models in this verification subfolder. So at this stage, we can consider step 1 done. And we're going to be right now using the Abdul verification test as our sort of our example for now. The next thing that we'll do is we'll run a series of executables. So step 2, 3, and 4 are different executables. And these executables really are what HydroGeoSphere is as a program. The first executable is called grok.exe. And what it does is it's a preprocessor. It will read the model input file. It's going to go through this file line by line by line. And grok.exe understands and recognizes what every line, what every command is meant to do. So grok.exe reads this file, and in a nutshell, what it's doing is it's preparing the matrix of equations. phgs.exe is the next executable, and what it does is it actually solves the system of equations. This is the actual numerical simulator. As phgs.exe runs, it's going to produce a wide range of different data files, many of which are going to be binary, which means we can't necessarily immediately open the files and begin to review the outputs. It does this because HGS produces a lot of data, and so generally we want to write data to a binary format which won't take up a lot of space on your computer. So the third executable, HGS to VTU, it basically reads those binary files and packages them up into a series of files which can then be loaded into a visualization product. So that's step 5. We will basically review model outputs. So 3 key executables in the HGS workflow. grok.exe compiles the grok file. It prepares the information for HydroGeoSphere. phgs.exe is the actual numerical simulator. This really truly is what HydroGeoSphere kind of the simulation engine is. And then HGS to VTU is a model post-processor. Takes the model outputs, reformats them into a different format that can be read into a visualization product. You might notice this comments about HSplot here and here. HSplot is an older form or an older version of HGS to VTU. So HSplot currently, as of the June version of HydroGeoSphere, is still included on installation, but moving forward next month, we're actually taking it out, and only HGS to VTU will be available. So we're going to just leave HSplot aside. We're going to focus on HGS to VTU. Okay, so that's the 5-step workflow. Let's take this, let's go through it again. We'll kind of add a little bit more complexity, take a closer look at things. So step 1, configure and write the grok file. We're going to spend actually probably half of our time today really digging into the contents of grok files. But we can do a quick scroll through this Abdul grok file right now, and we'll at least kind of like review what the key components of a grok file are. Now, something I want to highlight is that I'm using right now a special text editor called Sublime Text. Sublime Text has a unique language package for HydroGeoSphere that is what's causing it to, this input file to have sort of a color-coded look to it. At the end of the day, though, these input files are just basic text files. I can open this file in Notepad, for example, and it's the exact same contents. The only difference is that there's no color coding. So don't be don't be intimidated by the fact that this looks a little bit like coding. It is a little bit like coding in many ways, but this is just a simple text file. It's not, we're not using anything particularly special here to read it. If we do a slow scroll through this grok file, we will start to understand the key components of what needs to be written into these files. What are the key ingredients for a hydrologic model with HydroGeoSphere? The first important thing is, and maybe I'll also point out that you can add comments throughout these grok files as much as you like. If you just add an exclamation mark, and then everything after that exclamation mark on a line-by-line basis is going to be ignored. Okay, so this can be really helpful for taking notes within grok files if you ever need to make different versions of your grok file, testing out different commands, or potentially just adding comments for your colleagues to read. So the first major section of a grok file is always going to be grid generation. A numerical model is always based on a mesh, right? The spatial discretization of the area of interest. Typically in HydroGeoSphere, we're going to define a two-dimensional mesh, a triangular element mesh, externally using a different program. There are many different options for that, and it will be loaded in or read into the grok file. Here, what we're doing, layer by layer by layer, is building up the vertical structure of our model mesh. And just like this, with about, I don't know, 20 or 30 lines of text here, the three-dimensional model mesh has been generated. Now, moving further, we will generally also find a general simulation parameters section. So this is where basically we're defining some simulation options. What units do we want to use for our model? Do we want the model to use the default common node formulation, or do we want to implement the dual node formulation as we typically recommend? Is the model going to be run in transient mode or in steady state? Here's another option, the finite difference mode. This will basically cause HGS to use a finite difference approximation to the finite element solution. And we also usually recommend this as well. So these are just simple commands that basically define the nature of the simulation that's going to be run, okay? Every model will also require us to define properties and parameters. So our governing equations of flow will always contain parameters that help to represent some real world phenomenon, right? Flow through a porous medium, flow through soil, is going to be impacted by the porosity and the hydraulic conductivity of the soil. So by one means or another, we need to map those properties and parameters onto the model mesh to represent the spatial distribution of different soil types. That's what's basically being done in this particular group of text here. Now this model is very, very simple. It's one homogeneous soil type, and so there's not really a lot of complexity to this part of the input file. Most models, this gets much more complex. Now this model also includes overland flow or surface flow. So here we're defining our surface flow properties. We're going to discuss later on more about the mechanics of how this actually works. So I'm just kind of glossing over it a little bit here. What we're doing in this part of the input file is defining initial conditions. So as you go to solve a system of equations, you always have to start with an initial guess of what the hydraulic head distribution will be within that hydrologic model. So here we're defining those initial conditions. And then as we move further down, we're defining a series of boundary conditions. So in this case, we have 1 critical depth, 2 critical depth, and then a specified flux boundary condition. Boundary conditions are mathematical representations of where water enters the model, how and where water enters the model, and how it exits the model. So every model requires some level of boundary conditions. As I mentioned earlier with HydroGeoSphere, the real physics-based approach, the sort of The principle of physics-based modeling is just rain on the model. Well, this boundary condition here represents rain. It's a specified flux of rain which is being applied sort of homogeneously to the top of the model. Moving further down, we now get into a section here where we're defining numerical simulation criteria. So what are the error convergence criteria? How many iterations are allowed for each time step? Adaptive time stepping controls, which dictate how the time steps will grow or shrink over the course of the simulation. We then finally get into defining model outputs. So what are the points in time where we want to have a snapshot of model results? Do we want more detailed model outputs at particular points in space, such as observation points or hydrographs? And we are now at the bottom of the file. So those are the key components, the key pieces or ingredients to any hydrologic model. You must have a mesh. You must define boundary conditions and initial conditions and material properties. You will likely want to define some model outputs, otherwise you're not really going to get any data to analyze after the fact. And then you'll need to define simulation criteria, the numerical aspects of how the simulation works. In this case, it's a short text file. It's just about 250 lines, and it defines the entire nature of that model. And if you wanted to learn more about that model, again, I would just refer you to the verification model, or the verification manual rather, which contains a couple of images that we can refer to. So this is basically the size and the shape of the model itself. We can see the discretized mesh here. It's just a simple, it's not even a channel, it's just really a ditch, right? And in this case, the boundary conditions are very simple. It's just rain is coming into the top of the model and it's going to flow downhill through the ditch and flow out of the model. Very simple. Most models get much more complex, of course, but this is illustrative of the kind of key components of an HGS input file. So, step one, again, it's easier said than done. There's a lot that goes into building a model input file, but step one is to write that text-based input file. Don't forget, there's over 30 example files that you can review as sort of blueprints to understand the structure and how you can build these models yourself. Step two is to run grok.exe, the model preprocessor. So when it comes to running any of these executables, the way you're going to do it is using the command prompt, which is this little black box down here. If if you're not familiar with what the command prompt is, in a nutshell, it is a way for you to provide instructions directly to the CPU on your computer. It's sort of one of the proto, early sort of components of using user interfaces on computers, like way back in the 80s, 90s. So the way that we're going to open the command prompt is we're first going to navigate to the project folder. The best way to open the command prompt is to just click in the address bar of Windows Explorer and type CMD and then press enter. So for example, we have our model here, or model folder. I'm just going to click in the Windows Explorer address bar here and type CMD and press enter. And so on my other screen here, this opened up. You'll notice that the active directory for this command prompt is the location of our model input files. So this is why it's the easiest way of loading these the command prompt for HydroGeoSphere. Frankly, you can also just from your search bar, you can type in command prompt and you can open it up. But if you do that, then the active directory is just your user directory. You would then have to sort of navigate through the command prompt to this location. Much simpler to just navigate to the project folder in Windows Explorer, launch the command prompt from there. Okay, so then what you're going to do is you're going to just type grok into the command prompt and you're going to press enter. And what happens next is that grok is going to look in the current folder for a batch.pfx file. And this batch.pfx file, all it really contains is the name of the grok file. So .abdul.grok, this file contains the word Abdul. Its only purpose is to help Grok figure out which file it needs to open. In this case, it's going to look for abdul.grok. So we type in Grok, we press enter, and what happens next is there will be a big flurry of text, and essentially if I scroll back to the top here, what Grok does, it does it very fast, is it reads through the Grok file. Starting from the very top of the file, it goes through line by line, and it encounters commands, read GB 2D grid, scanning 2D mesh for errors, no errors found, generate layers interactive, zone by layer, new layer. What it does is it reads through this file line by line, and it does what these commands are designed to do. So if you ever run into an error, if there's maybe a typo in your Grok file, what you'll end up seeing, and I can do this right here, is maybe I'll just delete a letter. And what I can do is I'll save this Grok file. If I ever make a change to the Grok file, I will have to save it. But if I try to run Grok again, I get this error, input error, halting execution, unrecognized instruction, and then it tells me the name of that unrecognized instruction. So this tells me, oh yeah, okay, I've got a typo that I need to fix. So that'll happen invariably to every new users. We're not perfect, nobody's perfect. We sometimes make typos. So I'll save the file again, run Grok, and this time we see a normal exit message. That basically means it was able to go through line by line. It got all the way to the bottom of the Grok file without any problems. Okay, it prepared the entire system of equations. Normal exit means you are ready to go on to the next step. So before you run grok.exe, there's not really going to be very much in the projects folder. After you run grok.exe, the folder will look a little bit like this. You'll see that normal exit message in the command prompt, and there will be a whole bunch of additional files in the project folder. And indeed, if I open up the project folder here, you can see that there's a bunch of extra files. Most of these files are basically binary files that describe the matrix of equations. There is one helpful file at this stage. It's the abdul.echo file. This file is .eco, as we call it, the echo file. It basically echoes back all the information from the command prompt to this file, except usually with more information. So if we scroll up to the top here, for example, we will see eventually a command, uniform sublayering. In the actual echo file here, it says uniform sublayering, and then it tells us that there are 5 sublayers. So there's many ways where this file is a little bit more detailed than what we see in the actual command prompt. The reason we have this file is because if I close the command prompt and then I open it up again, the information that was listed in the command prompt is gone, but it's still available here in the echo file. So this echo file should also just basically be a line-by-line sort of echoing of the contents of your Grok file, indicating that grok.exe was able to successfully read through the file and essentially construct the matrix of equations. The other really helpful thing about this file is that when you get that normal exit message, well, in the echo file, it reads as finished parsing instructions, but then you get a summary of final data set. So you're starting to understand that HGS has no graphical user interface. It's all based on text files. And so how am I going to easily know whether things are being done correctly, right? You might write a text file describing your model mesh with the expectation that your model has 14 layers, but you might not be entirely confident in that at this point. Well, the summary of the final data set here in the echo file provides you with a bunch of information that will help you to understand exactly what you're getting when you run grok.exe. So it gives you a mesh summary. It tells you how many nodes there are in the 3D mesh, how many layers there are. It provides you information on mesh quality statistics. So in HydroGeoSphere, we're mostly going to be working with triangular element meshes, and it's important that you have a high quality mesh. It's going to help the model to be more numerically stable. So you get some mesh quality statistics here. Moving further down here, you get a summary of porous medium properties, so the hydraulic conductivities, the specific storage, the porosity, the different variably saturated flow parameterizations. You get that for the subsurface, you get it for the surface. You would get it, if the model had channel domain, then the properties would be listed here as well. You get a summary of the boundary conditions applied to the model, and finally you get a summary of the flow solution, so the numeric side of things, and your output data, right? So where are we going to be defining observation points or observation wells? What are our output times, et cetera, et cetera. So this file is really helpful as an early stage sort of sanity check on when grok.exe runs. You can check the echo file to make sure that the results are what you expect. And this is early, more important early in the stages of a project, I would say. As you get more and more familiar with HydroGeoSphere, there may be less and less of a reason to really closely review the echo file, but it's certainly very, very helpful if you're ever running into any problems that need troubleshooting. If grok.exe isn't properly running, or if your model is failing to converge when you run PHGS, you can check the mesh quality statistics very easily in there, things like that. So, a lot of output files generated at this stage, mostly binary. The key output file at this stage is the prefixo.echo file. By the way, this prefixo.echo, what that's really meant to, you'll see this reflected in the manuals. Every project input file has a different name. So in this case, the prefix or the name of the model is Abdul. So in this case, we have an abdulo.eco file. This kind of nomenclature of prefix or prefixo is something that comes up a lot when in the HGS documentation and whatnot. All right, so we've run grok.exe. The model is prepared and ready to run. Our next step is to actually run PHGS. We run this the exact same way. We just open the command prompt, make sure that the active directory is the location of our model, and we type in PHGS and press enter. And HGS is going through time step by time step here. It's solving the system of equations starting from t = 0 all the way up to whatever our model last output time is. And in this case, it runs quite quickly. We eventually see this normal exit message, and this means that the model was able to successfully run. While the model was running, more and more output files are being generated in the project folder. So now you can see our project folder has gotten a lot larger. There are, in general, two types of output files that are created by HydroGeoSphere when you run PHGS. You'll notice that here we have these large batches of files that all have the sort of file type or the sort of extension 0001. So all of these files have 0001 as the file extension. Each file contains an individual variable, whether it be hydraulic heads or saturations or velocities. It's a record of an individual variable at every node throughout the entire model at a specific output time. And the 0001 indicates that this is at the first output time. So in this case, all of these 0001 files equate to t = 1 second. All of the files that have 0002, these equate to files that were written at t = 300 seconds, and so on and so forth. So going all the way down here, we eventually get down to a set of 0009 output files, which are at t = 6,000 seconds. So these output files here, if I try to open them up, they're binary. I'm not able to read the results. And this is where the next step in the workflow comes in, post-processing our model outputs. But in addition to these binary output files, again, each of which contains one variable at an individual output time across the entire model at every node, in addition to that, we also have a .lst file that will be generated. This .lst file, or the list file, is similar to the echo file in that it contains a persistent record of what was shown in the command prompt, okay, on a time step by time step basis. so that if I close the command prompt, I still have all of the relevant information. And what is actually shown in this list file, I think we can get into that now. So when I run a model, this may not seem extremely important at the early stages of your sort of journey with HydroGeoSphere when you're provided with models that are able to run quickly. But most models will require a little bit of troubleshooting. And so if I pause this for a second, so the model is in the midst of running, but I've just paused it here quickly. At every time step, you're going to see sort of repetitive information displayed here in the command prompt, but also recorded here in the list file. The information that's displayed is structured, and so as you begin to use HydroGeoSphere more and more, it will become more important to understand how to read this. Even though it goes by extremely quickly in most cases, in other cases it will take longer for this data to be generated, right? The model that we're running here is quite simple. So what is this output data? So it usually comes in three sort of steps, three chunks. The first is what we call the global target time update. This basically tells us overall how the progress of the simulation is going. So we are on time step number 14. The global target time listed here, t equals 600, basically tells us that HGS is at this stage, it's actively working towards t equals 600 as its next target. Because we've defined t equals 600 as an output time, that means that HydroGeoSphere must solve a time step exactly at t equals 600. So basically, it's working towards t equals 600 right now, which is the third of 9 target times. Then we get percent done, time, delta t, and t next. So we're 8.33% done, the current simulation. The current time is t equals 500. Our delta t is 100, and our next time, the time that we are actively solving for, is t equals 600. So that's the global target time update. It gives you this information at the beginning of every time step. We then get into the summary of nonlinear iteration. So when HydroGeoSphere is solving the system of equations, it's doing so using an iterative Newton solution procedure. The results of this iterative procedure are listed here. The important thing, I think, to note here are the del val and the res val columns. So here we have iteration number 0, 1, 2. So this is basically saying we've gone through 1, 2 iterations. And at each iteration, the del val and the res val, these are error or convergence criteria. They're basically, a measure of the numerical error in your simulation. We ultimately want these to be as low as possible. In our input file, we have defined a Newton absolute and residual convergence criteria. Del val is your absolute convergence criteria. Res val is your residual convergence criteria. As the solution iterates, as soon as one of these two criteria is satisfied, then the solution is considered accurate enough to move on to the next time step. So in this case, our del val of 5.02 e to the negative 2 is actually still larger than the absolute convergence criteria of 1 e to the negative 3, but the res val is less than 1 e to the negative 3, and so the solution is considered done for the current time step, at which point HGS will move on to the next time step. Sometimes, for example, if the current time step is a target time, which is the case here, we've just solved t equals 600, then you'll get this type of information written: saving heads, saving pressure heads, saving depth of water table, saving elemental water volumes. That basically indicates that a batch of binary files is being written. But at every time step, before we move to the next time step, HGS goes through an adaptive time stepping sort of update. Okay, so what this means, in general, in order to solve a simulation as fast as possible, you would want to take as few time steps as possible. If your simulation is 100 days long and you're taking 1 day time steps all along the way, then it will by definition require 100 time steps. But if your simulation can go from one time step, a 1 day time step, to a 2 day time step, to a 4 day time step, to a 10 day time step, you might be able to solve the entire system of 100 days in maybe 10 time steps as opposed to 100. So that's going to be a lot faster. So what HydroGeoSphere does is it wants to increase your time step size, but it also will defer to you as the user in terms of how it increases or decreases the time step over time. So you can imagine that if you have an active hydrologic system, going from 1 day to the next, there will be some changes in the hydrologic system. There will be an area where hydraulic heads increase, another area where hydraulic heads decrease. The sort of goalposts for how quickly the time step size will grow or shrink is based on a number of adaptive control variables that the user defines. So in this model, we've defined the head control of 0.5, a saturation control of 0.05, and a numeration control of 10. So that's where these target change variables are listed, 0.5, 0.05, and 10. We also have a default water depth, so surface water depth target here of 1,000 meters. So that's huge. It's not really going to be relevant. What HGS does is it loops over, at the end of the time step, it will loop over every node, and it will look for the node where there was the largest change in each of these variables. So for example, there was a max change at node 21,709, wherever that may be, of 0.13880 meters in head. By taking 0.1388 and dividing by 0.5, we get a suggested time step multiplier of 3.6. What this basically means is that if only head was considered, HydroGeoSphere would suggest increasing the time step by a factor of 3.6. And on the next time step, then the expectation would be that there was a maximum change of hydraulic head equal to 0.5 meters, which is basically our target. HGS will evaluate all of the available targets. In this case, the smallest time step multiplier is based on saturation. And so then HGS will defer to the smallest time step multiplier. So we've accepted the solution at time equals 600. Our next time step will be 1.558 times larger than the previous time step, which is right up here, 100 seconds. So we go to the next time step, and we see that the delta T is still 100. And the reason for that is because we've also defined a maximum time step of 100 here. So these time step controls, these are basically you providing guidelines to HydroGeoSphere about just how quickly time steps are allowed to grow or shrink depending on how dynamic the hydrologic solution is at any given point in time. So these targets, these control variables and the Newton convergence criteria, these ultimately are what are going to control the time stepping behavior of your model. So I'll leave it at that for now. This does get into a little bit of a, early on when you're learning about HydroGeoSphere, generally you'll have models that will run quickly and you don't have to worry about this too much. But as you build more complex models, invariably you will end up in situations where the model is it's struggling to converge quickly, or it's running slowly. And so being able to recall back this conversation about how the time stepping system really works might help you to better understand sort of how to optimize things. Okay, now, so we've run phgs.exe and we've seen how many or most of the output files are binary. I might also point out that, not all of the output files are binary. If you've defined an observation point, for example, then you'll also get just a simple time series output file here that, flags an individual node and records more detailed information at that node. We'll get more to that later. But most of the files, outputs that are generated at this point are these binary files, right? So then step 4 is to reprocess those model outputs so that they can be visualized in something like ParaView or TecPlot. So ParaView is a free, so well, maybe I'll start with TecPlot. This is a screenshot of TecPlot. It can be used to visualize the results of three-dimensional finite element models, whether it be HydroGeoSphere or other models related to computational fluid dynamics or whatever the case might be. TecPlot is quite expensive, so we also support ParaView, which is essentially an open source version of TecPlot. It does everything that TecPlot really does. In order to reformat our model outputs, specifically these binary ones, all we have to do is type in HGS-VTU and press enter. HGS-VTU will then take all of these binary output files and it will compile them into a series of VTU files, one file per output time. So there's 9 output times per model domain. In this model, we have overland flow or surface flow, and we have porous medium or subsurface flow. So in total, with 9 time steps each, so in total we get 18 output files. What we can do now is just quickly open up ParaView and visualize some of the results. So the easiest way to load data into ParaView is to simply grab batches of these files, so all of the same file type at the different times, 1 through 9. We're just going to drag and drop them in. Now currently nothing's showing because we have to activate an individual data set using this little eyeball button next to it. And we can now see our porous medium 3-dimensional outputs. Each of the data sets that we load up here can be visualized together. So for example, if we load in our surface data set, we can see that there. They overlap the same space, so there's a little bit of a visualization glitch here. So let's turn one of those off for now. But the visualization sort of mechanisms are the same for both. You first of all have this menu up here, which shows the different variables that can be visualized. Right now, what we're looking at is elevation to the groundwater table. Okay, so why don't we instead look at saturations as maybe a little bit more intuitive. Because these data sets are transient, they contain 9 time steps. We can use these buttons up here to scroll forwards or backwards in time and see how the hydrologic solution changes over the course of the simulation. We can also change the visualization sort of representation here. For example, I can turn this on surface with edges, and that helps me to visualize the actual 3D wireframe mesh, right? Or I can turn on, let's see here, we can turn on wireframe, which only shows the wireframe. It doesn't show the intermediate elements inside. Or I can turn on points, which basically visualizes only the nodes in the mesh. Or I could change it to points Gaussian, which basically just changes the way that they're visualized, like essentially their size. And again, if I want to display this in addition to my surface data, I can do that easily. The surface data itself also has different variables. Right now we're looking at log depth, but we can look at, let's say, velocities, right? And these velocities also will change over time depending on the how the hydrologic solution changes over time, of course. In ParaView, I can also mix and match different frames. So let's say I want to show my surface data here, and I can create a new frame below with a render view. And while this one is selected, I can turn on my porous medium data. And maybe I want to tie these frames together so that they have the same orientation. So I can right click here and just easily click link camera and just click over to the next one. So now wherever I change the visualization in one of these windows, it will map itself identically over to the other one. You can also use ParaView to do sort of derivative visualization products. So in order to create clips or ISO surfaces, for example, what I first need to do is I will click on my data set. You need to click this apply button first. And what that does, I'm not really, to be honest, exactly sure what that does, But I will say that once you click apply, it now allows you to use these buttons up here. So if I select my porous medium data, which is the stuff, the data that we see in the bottom here, I can now, select clip or slice. So why don't I just create a clip? I can zoom out here to help visualize where the clip will actually occur. I can change the orientation as I need. There are all sorts of settings here on the bottom in the properties window. And by the way, if you don't see any of these windows, you would just go to view and turn on different things like the pipeline browser or the properties window. They're all context specific. So the properties that I see here for the clip are going to be different than the properties that I see for the actual three-dimensional data set. So once I've oriented my clip and maybe I change some basic visualization properties, based on what the options available in this properties window, when I click apply, then it will actually apply that clip. So now I can potentially display the clip alongside, if I turn the data set for the porous medium on again, and maybe I can also add in a slice. So now I can visualize a slice and a clip at the same time within the same frame. Or potentially, if I wanted, I could create, the 3D visualization is always a little bit wonky here. But I could also potentially create, let's say, a new frame over here. And instead of having the slice down here, I could turn it off there, and I could turn the slice on over here. And then I can, again, just link the camera so that they're all sort of part of the same framing. The last thing that I'll highlight is that you can use ParaView as well as a time series visualization tool. So if I go to create a new frame and I select line chart view, perhaps I want to load in, so whenever you run HGS, in addition to your observation points and your binary output data, for example, there's also a water balance file, which is pretty critical output. It tells you the fluxes into and out of the model via different boundary conditions, the overall changes in model storage over time, et cetera, et cetera. So this file here is currently formatted for TecPlot. It has all this auxiliary data or information about the data sets themselves, for example, the units and the names of these different data sets. If I type in HGS to VTU --time-series-CSV, it will reformat this output file into a very simple CSV file. In fact, it will reformat almost all of these files. So the water balance file here is now reformatted to a CSV, which strips away a lot of that metadata and now just has the basic time series information. And this file can very easily be loaded directly into ParaView. So now I can start to visualize all of my water balance data. However, I choose, right? I can zoom in and zoom out on different data sets over time. So we'll turn off error percent perhaps, and I'll click view. How do I change? I think it's one of these buttons. Here we go. So now I can see how my different data set, my different water balance components change over time. And what I can also do here is I can change or create a new frame and look at the spreadsheet view for this data. So if I'm interested, I can sort of query this data, look at it over different time steps. Yeah, so there's, ParaView, a lot you can do with ParaView. We will probably leave it at that for now. You can use it to visualize your data, your model outputs in 3D and 2D, as well as time series and querying the data on a node by node basis using the spreadsheet viewer. If you have any more questions about visualizing in ParaView, feel free to reach out anytime. And then I'll also say that the comprehensive tutorial that I'm going to be showing you in just a few moments also has a dedicated section to visualizing model results with ParaView. So that's another great walkthrough that you can use as sort of a tutorial. Okay, I'm going to take a short break. This actually kind of brings us to a natural break point, I think, in the session here. So we've just done a review, sort of the key workflows, like the key executables in the workflow. We've reviewed key output files at each stage. The rest of the training session today is really going to be about the grok file itself, building that model input file. That's step one in the overall sort of 5-step workflow, but it's a critical and critically important part of the workflow that we've so far kind of glossed over a little bit. So I'm going to suggest we take a short 5-minute break. We can grab a glass of water, have a little bit of a bio break if you need it. And my clock is showing 2:32, so I'm going to get started up again here at 2:37 p.m. So I'll see you all in 5 minutes. Okay, 2:37. We can get started again. Now is also actually a really good time to take any questions. So I'm just going to take one more moment to pause. The floor is open. If anybody has a question and if they click that raise your hand button, I'm more than happy to unmute you. Or you can just type questions into the Q&A or the chat. Okay, no questions for now, that's fine. Please feel free to ask them as we go through here. So, yeah, the rest of the session today is really going to be a deep dive into sort of the structure and approach to defining an HGS model within the grok file. The grok file, the idea with a grok file is that basically all aspects of the model setup will be controlled through this file. It's based on an intuitive command-based language for model setup. It does have some similarities to coding or scripting in the sense that it is, frankly, a command-based language, but we try to make it as intuitive as possible. It has some similarities as well in the fact that you can apply comments as you go through for documentation purposes or to activate or deactivate different commands. And we saw already earlier how a typical grok file has several common sections or components. It starts with a problem description, then you have grid generation, general simulation parameters, material or properties and parameters definition, initial conditions, boundary conditions, numerical stuff, time step stuff, and then finally output control. So as we go through the rest of the training session today, I'm actually going to shift gears away from the verification tests. I'm going to close that model up. And I'm going to instead use as my primary sort of learning aid the HGS intro tutorial. This tutorial was included as part of the training materials included in that email that I sent to everyone yesterday. If you didn't get that or if you didn't download everything, you can also access this tutorial quite easily from our website. If you go to aquanty.com and you click HydroGeoSphere Guide for New Users, excuse me, the intro tutorial is one of the first things that you'll really see. Click this button, click this big button, and it will download this package. The package itself includes a detailed guidance document. This is about a 90-page tutorial, and it covers the entire HGS workflow. So far what we've seen is a kind of a limited view of the entire HGS workflow because frankly, something else that's important is the entire process of building the two-dimensional finite element mesh. We'll talk more about this in a minute, but in a nutshell, we recommend a program called AlgoMesh. There are many other options as well. You can define or create your 2D triangular element mesh using, for example, a program called Gmesh, which is free to use. It's open access software, open source rather. But yeah, this is something we don't really cover in today's training session, but we do have a dedicated video just for working with AlgoMesh on our YouTube channel, so I'll just refer you to that. But the tutorial, the guidance document itself, includes the entire workflow. So an introduction to the tutorial, the software, key concepts, and the actual the R5 catchment model. So this is the tutorial model itself. Then you get into section 2, which is building the model mesh. So again, using AlgoMesh. Then we get into part 3, which is writing the grok file. And because HGS is just a text-based input file, right, it doesn't really lend itself too much to interactivity. But this section of the tutorial gives you detailed sort of section by section information about key commands that you find, references to the reference manual and command descriptions and whatnot. So this is basically what we're going to be covering in the rest of the session today. Part 4 is all about running the model. So those executables that we talked about already. What happens when you run grok.exe? What happens when you run phgs.exe? Review of the key model outputs within the command prompt, reformatting the model outputs, reviewing all of the binary output files. So basically what we've covered so far. Part 5 is all about visualization. So there's a dedicated section here to visualizing data with ParaView. And then, part 6 is all about sort of next steps, recommendations, sort of a catch-all of additional information that doesn't easily fit into the rest of the tutorial. So the tutorial itself has this very detailed guidance document. It also has all of the input files that would be required to rebuild the model mesh in chapter 2. This, of course, does require a license of AlgoMesh. So you can request a trial. I can put you in touch with the developers if you like. But you actually don't need to go through that section of the model of the tutorial. All of the resulting mesh files are also provided. The R5 model folder here is a fully working model folder, provides you with everything that you need. If we open up the grok file, you will notice there's a lot of sort of grayed out text here. This tutorial guidance document, this input file, is heavily commented, line by line by line, basically describing exactly what every command does. So this is an incredibly valuable learning tool as well. And the tutorial that we have here is probably a little bit more representative of a real-world modeling workflow than any of the verification tests. The model mesh that we build here is all based on raster files, which is the primary building block for most real-world models that are based on a complex geological conceptual model. So the layer structure is defined in a more realistic sort of it's more representative of like what an actual consultant or researcher would do, basically, as opposed to simple box models. This model also includes both surface flow and groundwater flow, but it also has evapotranspiration. So it provides you with sort of framework and the overall blueprint for applying those most commonly applied sort of processes. It also has a relatively more accurate or realistic approach for defining material properties, again using raster files as inputs. So this file here itself is I would say very, very valuable tool for new HGS users. So part of your learning journey will just honestly be reading this file and working through the tutorial. So I'm going to use this grok file here as sort of the primary learning tool for the rest of the day here as we go through the remainder of our model, or not our project slides, but the remainder of our PowerPoint slides. So there are a couple of one question that I often get is there a particular order with which I need to define the major sections of a grok file? And there is two firm rules. Your input file will always have to start with a description, a problem description, or a project description. This can be as long or as short as you like, but it has to include at least one line of text, which is end title. Everything above end title is essentially just treated as a comment. It's an opportunity for you to provide just descriptive information about the project itself. It can be helpful for you if you need to revisit a model after a couple of years, or if you ever need to share it with a colleague, or maybe with me for tech support. So this is the first part of every grok file. This section ends with an end command. Once that is finished, you are immediately put into the grid generation section of the grok file. So the grid generation section is a unique part of the grok file that has a number of commands that can only be used in this context. And you can imagine that until you have a grid or a mesh, it's not really possible to map boundary conditions onto your model mesh or to map material properties onto the grid, right? Because you need the grid first. So following the problem description, you immediately have to define your grid. Here we have the command generate uniform blocks. And I usually like to take a moment here just to remind people that part of the process of learning about HydroGeoSphere is going to be keeping a copy of the reference manual at hand, because the reference manual contains all of the building blocks, the tools in your tool set. If you encounter a command that you're not familiar with, perhaps it's generate uniform blocks, you should take a moment just to look it up in the user manual. So if I find this command in the user manual, this is also a good opportunity to sort of decode sort of the structure of the reference manual itself. This solid line means that we are about to enter into the description of a new command. The command itself is always in this particular format, this large text. If a command requires additional lines of inputs, for example, in this case, the domain length and the number of blocks in the x direction, then they will be enumerated in a numbered list. So in this command here requires at least 1, 2, 3 lines of additional text. The information that must be listed on those lines of text is then listed here in the command description. So xlen, nbx, x0, these are 3 different variables. They are the domain length, the number of blocks in the x direction, and the optional origin in the x direction, which is by default is 0. Then this is just repeated essentially in the y and the z dimension. And then finally you get a plain English description about what this command does. It generates a grid for a rectangular domain made up of uniformly sized blocks. The grid is formed by subdividing the domain in the x dimension into nbx blocks, each of length xlen over nbx, etc., etc. So long story short, this command here creates the mesh at the bottom right that we see here. It's 50 meters long in the x direction, subdivided into 100 sort of cells. It's a cross-sectional model, 1 meter wide in the y dimension, 1 cell, and 25 meters in height, divided into 50 cells. So this single command defines the 3D mesh, at which point the grid generation section is done, as signified by this command, end grid generation. By the way, the key word really is just end. It doesn't have to be end grid generation. End really is the operative word. When HydroGeoSphere, when grok.exe sees end, it immediately goes to the next line. So grid generation can be as simple as that. In general, it's going to be a little bit more complex. So here's a slightly more complex grid here. And this is an example. The text that we see up here, generate blocks interactive. If we scroll all the way down to the bottom, we see an end command. This is an example of what I call a command block, not because it's generate blocks interactive, but just because it's, I don't know, I need to find a better word, but basically it's just a number. It's a command that is book-ended by an end command. And in that context, there may be unique commands that can be used here. So the grid generation section of a model, of an input file, is generally the most structurally complex section of a grok file where you have multiple nested sort of commands. In this example, generate blocks interactive. Once again, let's just take a moment to quickly look it up in the manual. So End. This is our indication that this is a command block that needs to be bookended by an end command, as we see here. It causes grok to begin to read a group of interactive blocking instructions until it encounters an end instruction. This group should contain at least one instruction for each of the principal directions. Those instructions are grade X, grade Y, grade Z. And grade Y and grade Z, they work the exact same way as grade X, just in a different direction. They each require one line of additional input, and there are 1, 2, 3, 4, 5 individual variables for each one of those lines. So x1, x2, these are the starting and ending x coordinates, the starting element size and element size multiplication factor, and the maximum element size. In a nutshell, what's happening here is starting from x equals 75, right around here, and all the way down to x equals 0 down here, we will start with a cell that is 0.01 meters wide. Each neighboring cell after that will be 1.5 times the width of the previous until they reach a maximum width of 5 meters, which is kind of what you see around here. This is then repeated. There's 4 instances of grade X, 2 grade Y, and 4 grade Z commands here. And the end result is the mesh that you see on the right here. So this is slightly more complex, but in the grand scheme of things, still an example of a pretty simple grid in the world of HGS. It's defined entirely locally without the need for any exterior or like third-party software or anything like that. So these are sort of common grid or simple grid generation commands. But more often than not, more complex meshes will require third-party tools. So we do recommend AlgoMesh. In HydroGeoSphere, a high-quality mesh is really, really key for the numerical stability of your mesh and to improve model runtimes. In our professional experience, having tested many mesh generators over the years, AlgoMesh is really the best on the market. You can purchase it from us as well. If you are interested in buying HGS, you can just get a license of AlgoMesh on the side. But there are other options as well. So Gmesh, for example, GMSH is an open source alternative to AlgoMesh. Generally, though, the procedure for building a mesh in HydroGeoSphere starts with an externally generated triangular element mesh. So it describes the distribution of triangles in 2 dimensions, as you see in the image to the top right. Then we will import this 2-dimensional mesh into HydroGeoSphere and start building out the layer structure of the mesh for that 3rd dimension. And that is usually done using a command called generate layers interactive, which we see an example of here. In this case, we're not using an externally generated mesh. We're using a command called generate uniform rectangles to define a simple cross-sectional model that's 125 meters long in the x direction and 1 meter wide in the y direction. And then we use generate layers interactive, which is again a command block that has to be ended. And then in the context of generate layers interactive, we also support multiple additional types of command blocks: base elevation and new layer. So new layer has to be ended, new layer ... end. As we define new layers, there are other commands that allow us to define the actual elevation of these layers in different ways. So in this case, we're defining the base elevation of the model, z equals 0, using an elevation constant. And then to define the first real layer, now we know the bottom of the model is at elevation of 0. To define the first layer, we really have to just define what the elevation of the top of that layer is. So here we're defining an elevation constant of 19. We're also using a command uniform sublayering, which automatically just takes that new quote-unquote layer and subdivides it into 15 sublayers. Now, in the grand scheme of things, this sublayering term is just a term of convenience. Really, we just have, at this point, 15 layers, okay? So at the end of the thing here, when we have another 15 sublayers applied here, the end result is just 30 layers. It's not 2 layers with 30 sublayers. We just have 30 layers. The second sort of overall unit or section of sublayers is defined using a command called elevation from XZ pairs. And so we then have an include command which basically points to a different text file, and this text file here would simply contain a series of XZ pairs. You know, at x equals 0, z equals 25. At x equals 10, z equals 22.5. And then maybe a series of XZ pairs that more accurately sort of represents this pothole shape. And basically, the coordinates of individual nodes is determined, or I should say the elevation of individual nodes is determined by just interpolating values from this XZ list of XZ pairs. So the end result is the mesh that we see on the right. Now, the images that we're seeing here are actually representative of the R5 tutorial model. So we can open up that grok file here and start to take a look just at the general structure of how this works. So first we read in a 2D mesh from AlgoMesh. And something else I would like to just quickly, a sidebar here. I'd like to point out the usefulness of relative file paths in HydroGeoSphere. So in our project folder, we have a subfolder called mesh. And inside that folder is where we actually have the R5_mesh output file from AlgoMesh. So this is the actual file that contains the 2D triangular element mesh. Rather than typing in the full address of this folder, which is not recommended, because if I ever needed to, transfer this file over to a different computer, then I would need to update all of the file paths. Instead, we can use this relative file path. So ./ is basically shorthand form, and it means from the location of the current folder, look for a subfolder called mesh. If you have potentially a series of data files describing the model mesh, but you're going to end up building many, many iterations of the model, so you don't want to necessarily duplicate the data within this folder over and over and over again. What you can also do is you can save some data outside of the actual project folder, and the relative file path then would just be // mesh. So basically what that means is // means go back a folder, and then we should find a folder called mesh. Or if we wanted to do this again, for whatever reason, we're doing many, many iterations of our model. Maybe I save this right onto my desktop, I guess would be the next parent folder. Then what we would do there is just // mesh. And so all that means is from the location of this project folder, go out one folder, then go out another folder, and we will find that, okay, I don't know what's going on here. We will find that mesh folder. Okay, so for now, I'm just going to put everything back to where it was. But these relative file paths are very, very helpful. So we start by reading in our 2D mesh. Then we start to generate layers interactive. And what we're doing in this example here is we're just using the command elevation from raster, and we're feeding in raster files. Raster is, of course, a gridded data file. It can contain, in this case, elevations. It might also contain a distribution of property zone numbers or spatial distribution of precipitation rates. Raster files are very commonly used in HGS to define a lot of different spatially varying sort of pieces of the HGS model. So here, this raster file here just contains spatially varying elevations for the base of the model. We have this minimum layer thickness with fixed top elevation command, which we'll come back to in a second. But what we're doing now is we're just using this new layer command repeatedly, using the elevation from raster command to stack one raster file on top of another. And that basically is how we describe or define the entire structure of our model mesh. There is an offset top command here being used. So we have this file here is our ground surface. We're using it here to define the layer below the ground surface as well, by using the offset top command. This will, by definition, result in the creation of a layer divide, like a node sheet, going from one layer to the next, exactly 1 meter below the ground surface. And as we go through here, we're uniformly sublayering many of these, and we also now have a proportional sublayering command, which kind of is illustrated here. So basically just putting raster files one on top of each other with a bunch of these uniform sublayering commands. The proportional sublayering command basically indicates that in this case, there will be 3 model layers at the top, and the first and the second will be proportionally the same thickness, 1 to 1, and the third layer will be twice as thick as the ones above. So that's what results in this sort of layer structure here. Again, elevation from raster is pretty ubiquitously used by our user base to define spatially varying elevations. And not only elevations, but again, all sorts of different parts of the HGS model, whether it's the distribution of different property zone types, land use classifications, precipitation rates, or oftentimes also you can apply material properties like hydraulic conductivities directly using raster files if you've, for example, interpolated a bunch of different borehole data in GIS or something like that. So this is a screenshot from the R5 model that we've just been looking through, so kind of gives you the whole picture all at once. In HGS, just keep in mind that you always define your model mesh from the bottom going up. So the first command, base elevation, applies to the bottom, and then the next raster defines sort of the next layer up, and then above that, and above that, and above that, and so on and so forth. Something else that's not quite apparent from this image is that there's a really thin layer. It's right where my mouse is kind of hovering here. This layer is somewhere in the interior, there's a clay lens. So it's not really a continuous geologic formation across the entire model area, but there is this clay lens that is going to be hydrologically, important to the overall flow solution. So using the command minimum layer thickness with fixed top elevation here prevents rasters from pinching out. So for example, this slide just basically illustrates what happens when there's a raster pinch out. So if your raster files ever intersect, it's not possible to have a negative layer thickness or a 0 layer thickness. The layers must be continuous throughout the entire model. So if there's an area like this where one raster intersects and goes, a lower raster intersects and goes above what should be an upper raster file, that's what we call a pinch out. The command minimum layer thickness with fixed top elevation will automatically fix that by pushing the lower raster elevations down by the suggested minimum thickness. The last thing I'll point out here as well is that we have the command elevation from raster sort of described in the tutorial model, but there's also a command called elevation from raster CV mean, where instead of just sampling the raster file directly and applying the elevation of an individual node based on the grid cell of the raster that it lands in, instead the CV mean option uses an area weighted average of raster elevations over the nodal control volume itself. So this can result in a smoother mesh, especially in areas, with really large watershed scale models. You can have really potentially really spiky sort of reliefs. You can have really a difficult time sort of really representing in alpine areas like a smooth elevation contour. So this elevation from raster CV mean can really help with that. So yeah, this I think kind of covers the mesh generation. I'll also just mention, I've mentioned already, raster files are very ubiquitously supported in HGS. We also have pretty good shapefile support, so it can help you to select different components or parts of the model mesh, whether it be points, polylines, or polygons. AlgoMesh also allows you to use chosen nodes or chosen elements files, and these are kind of like based on the model mesh that you've defined, for certain nodes, right, that are basically baked into the mesh. The structure of the mesh itself, if we go back up here, if we're in AlgoMesh, right, I can select individual nodes and then save those for reference later in my grok file. Generally, though, it would be preferable to use shape files. So rather than using like a chosen node file that selects some nodes based on the current mesh, we could just use a polygon that defines a polygon and inside of which all of the nodes would be selected. That polygon is going to be independent of the mesh itself. If we ever need to update our model mesh, then we would also need to update any of the chosen nodes or chosen elements files that are associated with that mesh. So in the tutorial that we're looking at today, we are actually going to see a few areas where AlgoMesh files are used. So for example, here, we're choosing elements which delineate the location of that clay lens that I mentioned before. The next time I update this tutorial, I'm probably going to swap these out for shape files, because that's just generally best practice. The shapefile itself is not tied to the structure of your triangular element mesh, whereas these files are. So if I ever needed to update the triangular element mesh for this project, I would need to recreate this file for that new mesh, whereas a shapefile wouldn't need to be updated. The next section of your grok file is usually quite simple. I recommend going into the general simulations parameters or the simulation control options section. These are typically just one-line commands that, again, define the sort of nature of the model itself. What are the units? Do we want to run saturated versus unsaturated flow, transient or steady state? The dual node formulation, which I mentioned earlier, we have a version of this command for all other model domains. So if this model included channels, for example, then I would include the command dual nodes for channel flow, or dual nodes for fracture flow if my model had discrete fracture networks, for example. This finite difference mode, integrated finite difference for overland flow, remove negative coefficients, and no nodal flow check, these are generally recommended for all models. They are in general just going to make the model a little bit more numerically stable and or improve model runtimes. So you can look into what these actually do in the reference manual, of course, but in general, we recommend including sort of everything that you've got listed here. So that section of the grok file is quite simple. The remainder of the grok file, the remainder of building your model mesh, whether it's defining property zones, boundary conditions, initial conditions, it all requires you to be able to confidently select the right components of your model mesh. So it's also important to just know what those components of the model mesh are. The nodes in your mesh, of course, are the primary point in space where your governing equations of flow are being solved. They're sort of the basic building block of the model. In this image, the nodes, of course, are the red dots. Every neighboring node is going to be connected with a one-dimensional straight line segment. Okay. Sometimes boundary conditions will be mapped onto segments, and other times model domains such as the channels or tile drains or wells, these will also be mapped onto the segments themselves. So that basically means that if you want to build channels into your model, you want to make sure that you have segments that follow along the exact location of those channels. So then we have faces, which are two-dimensional shapes, either square, like rectangles or triangles, that are bounded at the sides by segments and at the corners by nodes. Again, boundary conditions can sometimes be mapped onto faces. Other times, material properties will be mapped onto faces. For example, the surface domain is a quasi-three-dimensional domain that is comprised of two-dimensional faces that sit on the top of the model. And then, of course, you have three-dimensional elements, right, which are bounded at the sides by faces, the edges by segments, and the corners by nodes. So then the other thing to keep in mind is that the vertical structure of the model mesh is based on layers, which are laterally connected elements, as well as node sheets, which are laterally connected sets of nodes. And these layers and node sheets extend all across the entire model domain. Different commands will require you to at times define or identify node sheets or layer numbers. For example, if you want to use a shapefile to select all of the nodes inside of a polygon, the polygon will define sort of the X and the Y dimension, right? Spatially where that selection occurs. You would likely also need to define the node sheet range, upper and lower, where you want that selection to be made. The reference manual has one of the lengthiest sections is dedicated entirely to options for selecting mesh components. So if we open up our reference manual and we go to section 2.4, we will see here that there's a subsection on selecting nodes, selecting segments, selecting faces, and selecting elements. And if we just scroll through, only the subsection on selecting nodes here, I think it's like the last time I checked, it's like 14 pages long. So there's a lot of different options on how you can select a particular node, right? There's a lot of different ways to do the exact same thing in HydroGeoSphere. I could use a shapefile to select a bunch of nodes, or I could choose a bunch of nodes based on the zone number that they sit in. I can choose nodes using a polygon shapefile. I can choose nodes using a shorthand form like choose nodes top boundary, which chooses all of the nodes around the top edge of the surface flow domain. I can use a command like choose nodes XY sheet list, where I provide a list of X and Y coordinates and a sheet number, and it will select all of those nodes. So there's a lot of different ways to do the same thing. It all really depends on user preference. You can use shapefiles extensively. You could use coordinate lists or node lists extensively. It really is up to you. But this is really, again, it's an important sort of piece of the puzzle in terms of building your model. So that section of the manual, section 2.4, it's definitely worth doing a scroll through and sort of seeing what the different options are. Okay, so now we get into defining material parameters or properties, and I usually like to start by just a quick clarification when I say model domain. Sometimes people take that to mean, you know, the spatial area of the model, which is not necessarily incorrect, but in the world of HydroGeoSphere, we also use the word domain to sort of refer to the collection of nodes that have a distinct governing equation. For example, the subsurface or the porous medium domain is where we apply 3D Richards equation. Then we have the surface domain. It's a collection of nodes that sits at the top of the model, where we are applying that diffusion wave equation. Then there's, you know, the fracture domain, which can be mapped onto the faces of the model, or the channel domain, which is mapped onto the segments. And these all have their own sets of governing equations, right? So given that they all have their own governing equations, they're all also going to have their own set of material properties and parameters that will determine how water moves through those domains. In order to activate a domain, you can use this command here, initialize domain. By default, the porous medium domain will be active as soon as you generate a mesh. It's assumed that, you know, HGS is going to be working in the subsurface. So the moment your grid is created, by definition, the porous medium is going to be a part of the model. But any other part of the model, any other model domain, whether it's surface flow, fractures, channels, evapotranspiration, you need to initialize it, and that is done by parameterizing it. So, for example, I can select all the faces on the top of my model, apply those faces to zone 1 in the surface, and then read some parameter values, a Manning's friction coefficient, for example. By going through that process, HGS will recognize that surface flow is a part of the simulation. I have to do this for every model domain that I want to use besides porous medium. This command here, initialize domain, can really help you to do that in a quick and easy way, but it will only apply default parameters. So you'll always need to apply your own parameter values based on the needs of the current project. So typically in HGS, we're going to be running subsurface flow, surface flow, and often evapotranspiration. And what that means is when you go into defining material properties and parameters, you need to kind of come prepared with a conceptual model, kind of like what we see here, which delineates the geographic or the spatial distribution of different soil types or hydrostratigraphic zones, different superficial soil types, different land cover classifications, or potentially crop type information and how that impacts, evapotranspiration. As well, once we get into boundary conditions, you also need to have sort of an understanding of where water is supposed to come from and where it's supposed to go in your model. So that's all part of a conceptual model as well. So a lot of this is going to be done, you're going to have to do a fair bit of data preparation in GIS typically beforehand, trying to understand the distribution of your model layers. Within each model layer, what's the different distribution of different soil types or different land use zones, things like that. The recommended approach for defining material parameters and properties in HydroGeoSphere is to first create what we call a material property file. A unique material property file is supported for each model domain. There's the mprops file for the porous medium or the matrix, oprops file for overland flow, excuse me, dprops for the dual continuum, fprops for fractures, all the way down to etprops for evapotranspiration. As you look through section 2.8 of the reference manual, which is called Materials and Material Properties, you will generally see sections or subsections that kind of align with the different model domains: porous medium, fractures, dual continuum, wells, tile drains, channel flow, surface flow, evapotranspiration. At the top of each section, there's going to be a table that lists the default parameter values that are applied in each model domain. So if you initialize a model domain and you don't apply some parameter values yourself, this is what you're going to get. And it's not recommended, right, to use default parameter values. It should be based on your understanding of the real world setting that you're modeling, right? This default Manning's roughness coefficient, I mean, don't quote me on this, but this might be representative, let's say, of a grassy field. But you might be modeling an area that has, like heavy agriculture or an urban area. So it's going to, require a different Manning's roughness coefficient. But the subsections within section 2.8 at large will list all these default values, and that can give you a good understanding of what parameters you need to actually apply to your models. And as you go through this section, you'll see commands that can be used to define individual parameters. And this section of the manual has sort of a special thing where it will list the scope of where this command can be used. It can be used in the grok file, or it can be used in the mprops file in this case. And these material properties files, okay, the point of these files is to name and define the parameters associated with particular quote-unquote materials. In the subsurface, a material is basically like an individual soil type or a rock type that has its own distinct parameters. In the overland flow or the surface domain, a material might be one particular land use classification. So if we open up our example model here, and we'll just take a look at like the mprops file. So this file here contains, right off the bat, the words medium sand. And if I scroll all the way down, that medium sand is ended. Everything up to the top here is basically defining what a medium sand is. We are defining a medium sand as having this isotropic hydraulic conductivity, this porosity, this specific storage value. We are also defining a relationship between saturation and relative hydraulic conductivity, as well as a relationship between pressure head and soil saturation. So these two tables of data here define a realistic range of saturation down to 18%, where relative hydraulic conductivity is 4.4 e to the negative 4 times our saturated hydraulic conductivity. And the saturation here ranges from 18% all the way up to 100%, where our relative hydraulic conductivity is just 100% of saturated hydraulic conductivity. Simultaneously, our pressure head to saturation relationship ranges from 18% saturation at a pressure head of -5 meters, all the way up to a saturation of 100% saturation, which is by definition sort of at the water table, where pressure head is equal to 0. So all of this data here exists to define what is a medium sand in the context of Richard's equation. Okay. Scrolling further down, we also in this project have a coarse sand, which is defined in much the same way, just different values. And then we have a clay. The clay has its isotropic hydraulic conductivity, porosity, specific storage. In this case, the unsaturated flow relationship is based on the Brooks-Corey function. Okay, so the Brooks-Corey function or the Van Gunukten function can be defined if you don't have access to this type of tabular data. There are some other commands here as well. I'll leave you to read these files a little bit more carefully, but there are commands in HGS, for example, generate tables from unsaturated functions that will cause the Brooks-Corey function to generate this type of tabular data. So you'll want to read into this section of the material properties file. So this file here defines 3 quote-unquote materials for the subsurface: a medium sand, a coarse sand, and a clay. If we look at the OPROPS file for our particular project here, we will see that it has 2 materials, a material called grassland and another material called ranch road. The materials themselves are user defined. HydroGeoSphere doesn't have a dictionary or anything in the background where it knows what grassland is. The user defines the material name and the associated parameters. These definitions, these names, are then referenceable in the grok file itself. So here we're getting into the actual nuts and bolts of how we map those materials onto the mesh. The way that this is done is first by defining property zones. So I'm going to come back to my PowerPoint here. We'll come back to the example in a second here, but what we do first is we map property zones onto the model mesh. So we might say all of layer 1 is a medium sand. Okay, we'll call it zone 1. And then all of layer 2 is coarse sand. Call it zone 2, just as an example. There's a lot of different ways that you can map property zones on. What you would do then is you would make sure to use this command, use domain type. This ensures that we're actively manipulating and working on the correct model domain that we want to actively work on. We then use the command properties file to basically point grok to the location where it can find those named quote-unquote materials. We will then choose a zone. In this case, we're choosing all of the zones, and we read the properties. In this case, Borden sand field scale digitized. This would be a named entity in the obdul.mprops file. Here's another example where we're getting a little bit more detailed here and also showing the zone assignment. A lot of different ways of doing the same thing in HGS, remember. So here we're saying, okay, use domain type porous medium. Choose all of the elements within this coordinate block. So from x equals 0 to x equals 125, from y equals 0 to 1, and from z equals 16 to 30, plus this follow-on selection, and apply them to zone 1, new zone, zone 1. We clear our elements. We then do a different selection and apply it to zone 2. And then over here, in the material assignment, we use domain type porous media, define the property file, clear our chosen zone, choose zone 1, read the properties, clear our chosen zone, choose zone 2, read a different set of properties. So here, clay and Borden sand field scale digitized, they would both appear in this file module5.mprops. The other thing to just quickly highlight here is the ubiquity of clear commands. Grok will always keep your previous selection in memory. So whenever you're choosing a new zone, it's always a good idea to clear your previously chosen zone. Or here, for example, After you're finished choosing these elements and creating a zone, clear those chosen elements before you move on to the next selection. So the property file itself, again, the contents are determined based on the needs of the governing equation itself, right? So there will be different properties in a porous media property file than there would be in an overland flow properties file, and an even different set of properties for, an evapotranspiration properties. So in this example, we have an evaporation depth, a root depth. These decay functions determine how the root density and the evaporation distribution function vary over elevations or over depth. Leaf area index tables, and then a number of different fitting parameters. So the needs of the governing equation determine the contents, right, of these property files. Let's just take a quick look at how it's done here in the R5 tutorial. So in the R5 tutorial, we're using a raster file here to define the distribution of property zones. So this pmzones.asc file, it contains a raster file that has 1s and 2s in it. So we clear our chosen elements, we choose all elements, and we read zones from raster. So now the entire model has a set of 1s or 2s, depending on, where the element falls with respect to the raster file. We clear our chosen zone, we choose zone 1, we read the properties of a medium sand from that material property file that we saw a minute ago. Clear chosen zones, choose zone 2, read the properties of a coarse sand. And these definitions can always be overwritten, so what's happening next is we are clearing chosen elements. Here we're choosing elements using an AlgoMesh output file. Earlier I had mentioned how it might be better to use a shapefile, but again, there's multiple different ways of doing the same thing. This file here delineates the selection in the X and the Y dimensions, so this 5 and the 6 is basically the vertical extent of the selection, so using a node sheet top and a node sheet bottom extent. So we apply that new zone into zone 3, and we choose zone 3, read the properties of the clay. And that defines the spatial variability in material properties for subsurface flow in this model. Now let's repeat for the overland flow properties. Here we're using the domain type surface. We read in a different property file for the surface. What we're doing here is we're choosing all of the faces on the top of the model and applying them to zone 1, and then reading the properties of the grassland. And in this case, we're choosing a set of elements based on an AlgoMesh file again, applying them to zone 2. So previously these elements here would have been in zone 1, but now they're in zone 2, and now we're choosing zone 2 and overwriting the previously defined grassland properties with the ranch road properties. And this is the general recommended process for defining material properties in your models, at least for new users, right? Define all of the distinct, unique, quote-unquote materials in the model within the associated material property file, and then use raster files or shape files or whatever means you like to map out a distribution of zone numbers throughout the model mesh. Then you choose zone 1, apply a property, choose zone 2, apply a property, choose zone 3, apply a property, and so on and so forth. Now we move on to initial conditions. Generally, from a functional perspective, applying initial conditions to your model is quite simple. There are a number of different options listed in section 2.6 of the reference manual. We've got a couple common ones listed here: initial head based on a surface elevation, or initial head from output file. So this allows you to restart the simulation using output from a previous simulation. This is a really key part of the HGS workflow. We call it model spin-up. Usually what you'll do at the beginning of a new project is you'll start the model fully saturated, and you can run it for an extended period of time using just net precipitation as the main boundary condition. Eventually the model will sort of drain to something that is representative of a long-term sort of average climate hydrological condition for your model. That output can then be used as sort of a starting point for subsequent transient simulations. You don't want to go straight from a fully saturated model right to running like a daily transient simulation over the course of 10 years, because the starting point for these transient simulations is going to be quite important. So, but again, from a functional perspective, it's usually quite simple. You're just going to use really one command usually to define initial conditions for the entire model, or at least for the entire domain. You do have to define initial conditions for both the surface and the subsurface if you're going to be applying both of those processes to your model. The example R5 tutorial is also quite simple here. What we're doing here is we're just defining an initial head for the subsurface based on a depth to water table of 1 meter. So our water table will be 1 meter below ground surface. And then in the surface domain, we're applying an initial water depth of 1 millimeter. Generally, we recommend setting a small value instead of a perfect zero. Zeros can sometimes just be numerically unstable. But again, even better yet is just use this as a starting point, run the model for a long period of time with net precip to spin the model up to, again, your sort of average hydrologic conditions for that region, and then use the command initial head from output file. And this just requires one of those binary output files, right? Okay, we now get to boundary conditions. Section 2.7 of the manual has all the details on boundary conditions. Before you create a boundary condition, there's an important note here. You have to create a set, a node set, face set, or segment set. A node set, face set, or segment set is simply a selection of some mesh component. For example, here we are choosing a bunch of nodes which define a set of segments, and we're creating a segment set and we're calling it outlet. So now we can reference this segment set when defining the boundary condition. So creating these sets is kind of like creating a zone. You're basically just, in this case, choosing segments, or if we scroll further down here, we're choosing all of the nodes on the top of the model domain, which by definition have defined sort of all of the faces on the top of the model. And we're creating a face set and we're calling it top. So then later when we go to define a rain boundary condition, where is it going to be applied? It's going to be applied to face set top. So it's just basically the process of selecting some mesh components and giving them a name to help you during the definition of the boundary condition. Then the actual functional sort of approach to defining a boundary condition becomes quite simple. It always follows this pattern where you have the boundary condition command, which is a command block. It has to be ... ended. Within the boundary condition command block, you will always define the type and either a node, face, or segment set. And most of the time, you will also define a time value table or a time raster table. We also typically recommend applying some options or constraints, although they're not necessarily required. So for example, here we choose nodes on the top of the model. We create that top face set. We enter the boundary condition command block. We use the keyword type to define the type itself. And the boundary condition types are all found in the manual. Under flow boundary condition types, you'll find several different subsections, but there's head, there's pressure head equals elevation, head equals initial, head offset. If we go down to specified flux, we have flux, we have rain, we have flux nodal. Almost every boundary condition type will also include a little snippet of a grok file here as an example to see how you would apply this in a grok file. Now, this is the easiest way of knowing exactly what type of set is required for each individual boundary condition. So a flux nodal is specifically applied to nodes. If we go up here to the flux boundary condition, we will see that it is specifically applied to faces. So we define the type, in this case as a flux, we define the face set, In this case, it's top, this previously created face set. And then here we have a time value table. So this is simply a table of times and values. This, for example, means that at t equals 0, a flux of 5.555 e to the negative 6 meters per second, which is equivalent to 2 centimeters per hour, will be applied. And that flux is going to be maintained indefinitely until the next time in the time value table. At t equals 3000, that flux goes to 0. If this second line wasn't here, then basically the initial flux would be maintained for the entire simulation. The time value table is then ended. We have an optional command here, TecPlot output, which we always recommend. It basically creates a TecPlot formatted output file with the nodal values of these fluxes. You don't always need it, but it's good to have, and it is easy to implement, a simple one line of text. So we generally recommend including that. And then you end the boundary condition, and that's it. You can then move on to potentially defining more boundary conditions. So a couple of tips and tricks here. First of all, the TecPlot output command, as I mentioned, it will create a TecPlot file, a formatted file, which tracks these fluxes on a node-by-node basis. So you might have a boundary condition that's applied to 10 nodes. You might need to, at some point, figure out exactly how much flux is being applied to one of those nodes. This file can help you to figure that out. You should really just apply it to all your boundary conditions. It's good to have that information if you need it. The other tip here, and I'm just noticing now that I have a bit of a blunder. I wanted to just move this this bullet over a little bit, but you should always consider ways to apply boundary conditions intelligently. So, for example, if you apply a flux nodal boundary condition to a node that is dry, HGS will simply try to remove water from an area where it doesn't exist. Many boundary conditions have constraints that you can apply, such as nodal flux reduction by pressure head. This is something that is applied as an option or a constraint to the flux nodal boundary condition. It will automatically modulate the flux based on the pressure head at that node itself. It will potentially turn the flux off if the node is dry. These types of things can often be the cause for your model to not converge on a solution. Another command that's helpful for boundary conditions is the scaling factor command. It is embedded in the boundary condition command block. It can be used to help you calibrate your model by scaling boundary condition fluxes up or down, for example, changing climate forcing data over time. It can also be used to perform unit conversions, right? So you can apply a scaling factor. If you have your base data from GIS or your weather data is in, let's say, in this case, we have an example where it's in millimeters per month. We can convert that to the project units of meters per second by applying this scaling factor. There is also a one-line command that can be applied to boundary conditions called interpolate, and it will cause the actual magnitude of the flux to be interpolated in individual time steps based on your time value table. So for example, the purple line here represents a time value table. At a certain time, your flux goes from, let's say, 1 up to 2. If you apply the interpolate option, then the actual magnitude of the flux that it's applied at each time step, these red steps, will be interpolated linearly from one point in the time value table to the next. So this allows you to have a more gradual change in boundary condition fluxes, which can make the solution more numerically stable. We now move on to sort of the penultimate section of the grok file, which is numerical settings. So fortunately, we talked about this a lot before. We don't really need to go over this in depth again. In terms of fine-tuning the adaptive time stepping controls, the numerical simulation criteria. But in general, you want to try to fine-tune your numerical settings for each situation. There's no silver bullet in terms of how your time step settings should be set up. So for example, if you're going through model spin up and you want the model to run for a really, really long time until it reaches that sort of equilibrium solution, right? That equilibrium watershed condition. This is the blue line. it might be fine for you to have really high solution error in the early time steps, because the only purpose of model spin up is to get to that sort of steady state condition, which can then be used as the starting point for subsequent transient simulations. So here you might as well just set your numerical solution, your convergence criteria to be extremely loose, right? That will allow the time step sizes to grow really quickly, and you can cover a lot of time really fast. And then once you get to this part, of the simulation, you can actually change these things during a simulation. So you could tighten the convergence criteria up to get lower error later on in the simulation, but just leaving it really loose initially to sort of boost things along, to kind of jumpstart the situation. So in this kind of situation, we don't really care what the model output times are, right? The model spin up might go for 100 years or 10,000 years. The main thing is we just want to reach some sort of equilibrium condition as fast as possible. So here, the time step sizes can basically grow unbounded, as large as possible, which will allow us to run the simulation for a longer duration, for a longer simulation period, faster and faster. But then you might get into a situation where you need to run transient situations, like a transient simulation where you have boundary condition forcing data, this green line, that changes maybe on a monthly or a weekly or a daily basis. These boundary condition times where boundary condition changes, this also plays into the concept of target times, which we talked about before. So target times are points in time where your boundary condition changes in value. So your time value tables, if I go back to the boundary conditions here, any time listed in a time value table automatically becomes a target time. Target times are also generated from the output times list. So when you define your output times in the model, so for example, here, these also become target times. So the target time list is made up of two things: these output times and points in time where boundary conditions change in size or in magnitude. The distribution of target times will by definition impact the growth of your time steps, because you need to land, the solution needs to land there, right? So you can't take a time step that goes past a target time. If you have a daily transient simulation, by definition, your simulation time step will only be able to be 1 day at a maximum, because your boundary conditions are changing day by day by day. So when it comes to numerical settings and trying to fine-tune things for faster model runtimes, you might need to look into also fine-tuning your target time list, fine-tuning those adaptive time stepping controls, fine-tuning the numerical simulation criteria. There's a lot of different factors that go into it. So yeah, target times are impacted heavily by boundary conditions. The interpolate option can be really helpful by moderating quick shocks to the system, right? So at every boundary condition, whenever something changes in magnitude, you'll generally see a bit of a spike in model error, and that can also cause the time steps to constrict. So there's a lot of moving pieces, but the more you experiment and run models, the more you'll see how these different sort of things interact with each other. So we've already seen an example. Earlier we kind of like took a close look at the output that you see when the model runs. If you ever need a refresher on that, you can check Appendix C of the manual. But in general, there are basic time step settings, things like your initial time step size, minimum and maximum time step multipliers, and the output times command, which specifies when a snapshot of results will be really taken. Then you have your adaptive time setting controls, right? Head control, saturation control, water depth control, and Newton iteration control are the standard ones. These are the variables that HGS monitors and tries to target the value that you've provided. If your head control value is 0.1 meters, then the time step will try to grow until heads are changing by 0.1 meters at a max from one time step to the next. So that's basically it for Oops, I have a bit of a repeated slide here. We then get into model outputs. And in general, there's two types of outputs or data that HGS is going to produce. There's the geospatial output files that we saw earlier, right? The snapshot of those binary output files that are created at each of the specified output times. But then there are also a number of additional user-defined outputs, which are not going to be generated by default, but they can be requested or defined as needed. For example, the creation of hydrographs, observation points. There's a whole bunch of different options there, and we'll see a couple here in the next few slides. In terms of those geospatial output files, again, they're the binary files. I will note that there is a bit of a way to read what these files contain. The formatting of the name of the file is this prefix O. So when we run the R5 model, it will be R5O, then a variable. If we go to the last slide, we have hydraulic heads, head, pressure head, saturation, velocity, depth of groundwater table, exchange flux, flow rates. So those are the variables that you'll see listed, and then underscore domain. So PM is short for porous medium. OLF is short for overland flow. CHAN, C-H-A-N, is short for channel. FRAC, F-R-A-C, is short for fracture. And then you have the output index time. So 0001, that's output time number 1. With respect to those user-defined output files, the most common are going to be observation points, hydrographs as well. But you can also, there's a lot to choose from. If you look in section, I think it's 2.12 maybe. Yeah, section 2.12 of the reference manual has a number of subsections here that will provide you with additional outputs, additional commands that will generate specific outputs that you can review here. So we've got some of the common ones here. There's observation points. It will typically flag an individual node, and a subset of the variables listed here will be recorded at every single time step, not just at user-defined output times, but at every time step. So there's many different ways of defining output or observation points. You can do them one by one. You can do them in batches. You can also define observation wells, which turn sort of groups of nodes into a single output file. This is what an observation output file looks like. There's a bunch of metadata here that is going to be primarily used for TecPlot. But we saw earlier how if we run HGS to VTU with that time series CSV option, it can reformat a lot of the outputs to be loaded easily into, for example, ParaView. But these are just text files. You can also just load them into Microsoft Excel and really process them however you like. So this is an observation point output file. The observation well output files are a little bit more complex because it sort of formats the data into blocks. So my recommendation for new users is if you have a well where you want to track the data for, let's say, 3 nodes that are stacked one on top of each other, I would just define them as 3 separate observation points. It's going to make it a lot easier to process the data because these are not formatted as simple time series output files like the observation points. Surface flow hydrographs, again, you generally are going to define these on like a fence of at least 3 nodes across a stream within your model. Again, you don't have to define the location of a stream. The stream itself will follow the topography, but if you have an area where you know water is going to flow, you just kind of create a fence of nodes and use this set hydrograph nodes command, and it will generate an output file that records the flow rates across that fence in both the surface and the subsurface. Soil water balance command is very easy to use. It basically just tracks the total volume of water within different parts of your model, in the unsaturated zone, in the saturated zone, and then at different depths within the model. The water table command will allow you to track the water table depth at different locations. There are a number of different polygon tracking commands that allow you to basically track a localized water balance for individual nodes or groups of nodes based on their nodal control volume area. Fluid volume, similar. And that pretty much brings us to the end of the, this entire grok file and the presentation essentially. So the R5 model here, again, I think it should be your next step as you learn to use HydroGeoSphere is to go through this input file carefully, review the associated tutorial guidance document carefully as you go through. It has more and more details, basically everything that we covered today, but potentially with sort of little bits of detail added here and there. In this file though, towards the bottom, so we've defined our boundary conditions. In this model we have a series of critical depth boundary conditions. A critical depth basically just means in the surface, water is able to flow out at that location, right? So we usually bound the entire surface of the model around the edge with a critical depth boundary. Then we have a rain boundary condition here, and we have a flux nodal boundary condition, which is basically the locations of some pumping wells in this model. And then here we have PET, so I'm going to let you look into PET independently. In a nutshell, we apply PET as a boundary condition, but then we also define the ET domain with it's a set of parameters and properties. The actual evapotranspiration rate will then be calculated based on water availability. We then get into time stepping controls here. One thing I do want to quickly note is that there are two errors that are in this model on purpose. You see here it says note there's a typo on this line. We already saw earlier what happens if there's a typo, so I'm going to go ahead and fix that right now. The other thing I'll note is that the convergence criteria for this model by default are set to be very, very low. This is to illustrate what happens when a model won't converge, and we'll see an example of that in just a moment when I go to run this. We've got our time step settings, and then we get all of our model outputs. And then at the bottom here, I have an additional section on particle tracing, but we're not going to cover that today. I see a question in the chat here from Aspen. So, okay, can I provide a little bit more detail on the reactive transport capabilities? Can HGS simulate multi-phase flow, phase partitioning? So the reactive transport capabilities of HGS are relatively simple. We support first and zeroth order reactions. We support chain reactions, although not branching chain reactions. You can have multiple solutes that are transported as advection, dispersion, diffusion reactions. Multiple solutes can be tracked in parallel, but you can't really have complex multi-component reactions, if that makes sense. In terms of multi-phase flow, really no capabilities there. It's all aqueous flow. There are commands that allow you to define not solid, but like non-aqueous phase liquids. You can basically set a certain amount of mass that can sort of dissolve into the aqueous phase over time, and it will be treated as basically an immobile sort of like an immobile store of solute that can just slowly release over time. But we don't really do multi-phase flow in the context of like aqueous phase flowing through the unsaturated zone and potentially degassing into the vapor phase and things like that, which I'm guessing is probably where the question is leading. So in terms of multi-phase flow, there's really not much to say there. So the reactive transport capabilities are, pretty run-of-the-mill, first and zeroth order with potentially multiple solutes tracked in parallel, but relatively simple, no complex reaction kinetics with multiple different solutes. We do support also density-dependent flow, which can be a product of like saltwater intrusion or seawater sort of simulations is one of the main use cases there, but it also can potentially be due to just really, really high concentrations of really any solute. The density-dependent flow formulation can also be sort of conceptualized for geothermal energy transport. I'm more than happy to have a follow-up call and we can kind of dig into some of those details if you're interested in that in particular. Okay, so we have here 5 minutes left. We have reviewed this entire grok file in some detail. And before we finish for the day, I'm going to run this model and illustrate one last thing, a bit of a superpower in the world of HydroGeoSphere. So I'm going to run grok, and when you guys run this, you'll get this error here. It's not really an error, but it's telling you there's no batch.pfx file. What's the name, the prefix of the problem file name? In this case, it's just R5. So you would just type in R5 and press enter. Grok runs no problem. Batch.pfx file is created automatically, so you don't have to type the project name or the project name in anymore. There were no warnings or issues raised, although when you run this tutorial out of the box, there will be a typo. Don't forget about that. Pretty simple fix. Just fix the typo, save the file, run grok. Now we're going to run phgs. And as I mentioned earlier, I'm just going to quickly pause this. I'm pressing the pause button on my keyboard here. The Newton convergence criteria for this are extremely tight. And so what's happening here is HGS is going through the maximum number of iterations, 12 max iterations, and it's failing to converge on a solution. And so what happens then is the current time step is cut in half. And this has already happened. It's been cut in half once, twice, 3 times before I managed to pause it. So the time step is getting smaller and smaller and smaller, and it will continue to basically do this indefinitely until the time step gets so small that you would basically be taking like less than a nanosecond time step at a time, at which point HGS just quits. It says, I'm not really able to solve this problem. Now, the solution here is simple. We just need to loosen these criteria up. The solution is not always as simple as that, but in this case, it does offer us a nice opportunity to highlight this debug.control feature. So at the start of every single time step and every Newton iteration, HGS checks this file and it sees the command debug off, which tells it to ignore the rest of the file. What we can do here is we can add a comment here, which lets HGS continue to read this file. Every other line is commented out, but I can start to uncomment lines, which allows HGS to actually implement some of these commands. The commands, as you can see, allow us to generate snapshots of output files. We can watch particular nodes. If, for example, node 5667 seems to be problematic, it keeps cropping up in my, as like this. These are the nodes that have the highest error, right? So if there's one node that keeps cropping up, it's likely there's a boundary condition error there, something's happening. But I can create a watch node list where I will get some additional information about this node, which can be helpful for troubleshooting. I can also change solver and Newton iteration convergence criteria on the fly. So the fix here, as I mentioned earlier, is simple. The fix is not always simple, but being able to modify the solution convergence criteria on the fly does allow you to do this. So we've instructed it to pause at every single Newton loop, and it paused, and then it managed to solve on the 7th iteration. It's also now pausing at every time step. So press enter. Paused on a Newton loop, press enter again, press enter, press enter. And it's now solved on the 5th iteration there. So I'm going to turn off the Newton loop pausing now because that's becoming tiresome. And now we can see that the solution is converging relatively rapidly. We already saw earlier about how the global target time is updated. We've seen how the adaptive time stepping really works. The main purpose of this little demonstration here is just highlight the potential usefulness of being able to modify convergence criteria on the fly. I'll turn this pause time step off. I'll save this file one last time. Now, when I hit enter, it's just going to carry on and it will continue to solve the solution. And it should only take a minute. Happy to take a moment to just visualize some of these results here once the simulation is done running. But I'll also just take this moment to thank everyone for joining me today. This is basically the end of the training session. I'm happy to stick around for a few minutes if there are any questions. I'm also available anytime via email. I'll put my email into the chat right now, bmcneil@aquanty.com. And encourage you really to reach out if you ever have any questions, big or small. I'm more than happy to answer questions as they come up rather than you having to potentially sort of look through these really large reference manuals searching for an answer. I'm here to help. That's my whole job, so don't hesitate to reach out. The model's finished running. I've just quickly run HGS to VTU, which reformats our model output files for visualization. I'll open up ParaView here and just quickly maybe close some of our existing layouts and delete some of the earlier data sets that we had. And in our R5 tutorial model here, now I have all of these .vtu files. So we've got our porous medium data here. So right now, take a look at soil saturation, see how that changes over time. We can also load in our surface data. Maybe see how surface depth changes over time as well. That's about it. You know, there's nothing too special in terms of visualization here that we didn't see earlier. So just quickly check the chat. Yep, that's the end of the training session. So I'm happy again to stick around for a couple of minutes if there are any questions. But if not, thanks one last time. I hope you did find this session informative and helpful, and I hope to hear back from you soon. The trial license that was provided as part of the course is good until the end of this month, so I hope you'll make the most of that. And I'll hear back from you before the end of the month. Okay, I'll end the recording now and make sure to get this loaded up onto YouTube ASAP.